박영수 교수님 혹시 계세요?
예, 지금 들어왔습니다.
네, 5분 후에
예.
그 교수께서 해주시면 됩니다.
예, 감사합니다.
네, 네.
준비하겠습니다.
예.
Hello everyone. My name is Enoch Park.
교수님 안녕하세요. 추워. 아, 시조과는 봄이겠네요, 지금 이제.
정각에 시작할까요?
Yeah, when you're ready, we can start. Yeah.
Okay. Hello, everyone. My
Hi.
name is Eno Park of Shizuoka University, Japan. Can you hear me?
Yes.
Okay. Nice to meet you. Professor Lee of Chungnam National University, Professor Chen of Shanghai University, Professor Tran of Penica University of Vietnam, and welcome all attendants of this little e-workshop, Biosensor 2021. I'm very happy to see so many of you here at today's International e-workshop on Biosensor 2021. COVID-19 has spread all over the world for just 1 year. Currently, 1 million people are infected worldwide, and 2 million people are dead. And a tragic pandemic still continues. We are living in a perfect closed world now. However, we are opening the closed world and communicating with China, Korea, Vietnam, and Japan. What a wonderful day today is. Let's share, enjoy today's workshop. And this e-workshop is a showcase for your research and activity. Today, 25 researchers and students will present excellent work, and among them, gold and silver medalists will be awarded. Please challenge. And also enjoy all day and ask questions without hesitating. Thank you again, Professor Lee, for planning this workshop. And thank the staff of Chungnam National University for technical assistance. Hopefully, we have no trouble Zoom meeting system until finishing our all schedules. And finally, I wish all of your research achievement is multiplied through today's e-workshop. Let's open our closed door from country to country, and we will get fruitful achievement from this international e-workshop. Thank you very much.
Yeah, thank you for the nice announcement. welcome announcement. I just, according to the schedule, I just want to just introduce the conference and presentation rule and award. Please just turn, give me the host. Then I want to share my slide. Oops. Yes. So can you see this slide? So this is the basic rule for the conference. So we are asking whole student use speaking English because the modern science and engineering usually use English rather than Chinese, Korean, and Japanese. So we want to improve the language skill. So please use speaking English. And number two, ask questions through oral or typing method. So some students want to use the typing, I mean the chatting. So you can simply use the chatting and in English, then that would be okay. But I recommend use oral question. And number three, at least one question should be asked from other countries. For example, if Korean presenters are speaking their work and the other Chinese and Japanese students ask one question to Korean student. And number four, at least one question should be asked from the next presenter. Yeah, so uh, then we can just to share the question. And number five, to keep the time. So we're going to provide the 1 minute left notice from the session chair. So for 20 minutes and 19 minutes, we will give some notice, and then 5 minutes talk and 4 minutes and 3 minutes talk, 2 minutes. Then you will simply know that 1 minute left. And number six, please select three students who have done the best presentation. So then we're going to give some award. So rule is like that. Korea select three Japanese students, Japan select three Chinese students, and Chinese select and three Korean students. Then please announce the names in the closing ceremony. So we want to just share our completion and also just achievement in the closing ceremony. And number eight, the award and small gifts will be delivered after the conference from Korea. For example, already last night we prepared the best research award like this. So please see the video. Uh, can you see this video? Hold on. Yeah, if you see my video, then I'm just showing my one award. So I'm going to provide this award to uh, your campus after selecting three uh, achievement. So that's the rule. The simple rule or will keep our conference in a better organization. So that's thing. So once again, Professor Park and Professor Chan and Professor Dan just accepted this conference. And even though we are under the pandemic, but we just will get over through the technical advances. So hopefully today, we are going to enjoy our research performance in the level of international community. So whole of the uh, uh, presentation will be recorded and also lively broadcasted in the world. So as you see the YouTube, you can just see the your voice directly, and all are just recorded, and so you can use it this recording for your resume in the future when you graduate. I really hope. And finally, uh, even though you feel nervous, yeah, I also a bit nervous. So just enjoy this presentation. Thanks so much. So let's start. Mm, now let's move on the first session for invited talk. Uh, Dark and Dr. Student. The session is a 15 minutes talk and 5 minutes Q&A. So session chair is me, and so 15 minute talk and 5 minutes questionnaire. And we are starting 10 tenths a bit 10 minutes earlier than scheduled. So the first presenter is from Shizuoka University. Then the present name is Akhilesh Babu Ganabonia. So he's talking about the roadmap to the dual modularity analytical testing of virus. So let's welcome him for his for hearing his talk.
Very good morning, Professor, and all my dear friends. Thank you for the brief introduction today. First of all, before starting my talk, I'm really excited for having this, being a part of this conference, because it's been a year because of this COVID pandemic. None of us are being able to share our research with the world or learn new things from others. So I'll just start. Before starting, let me share my screen.
You need to change your video. I mean the
I need to get the permission for sharing the screen.
yeah, please. Then you can start it.
Somebody need to stop sharing the screen.
Hold on. I need to give the authority to Yugong.
No, but when I'm sharing my screen, I'm getting you cannot share screen while other participant is sharing. So there is option for only one screen sharing.
Perfect.
Okay. Yeah, I can do it now. Okay. So before getting into the talk, the title of today's talk is Dual Modality Analytical Testing of Virus. So I will be talking about majorly virus sensing. So before that, let me give a brief introduction about myself. I am Akhilesh Babu Ganganboina, presently working as JSPS postdoctoral research scholar in Research Institute of Green Science and Technology from Shizuoka University. And I have done my PhD in biomedical engineering from National Tsinghua University in Taiwan, and continued postdoctoral research in the same laboratory for a few months, and then moved to Japan. And I have done my master's and bachelor's in biotechnology from India. So after gaining a lot of these experiences, I learned something about nanotechnology, which I'll be sharing today about my learnings. So before getting into the talk, so nanotechnology, this is the word which is being fascinated since last decade. So I believe that nanotechnology is just an invention from an old idea, like several basic elements like carbon, silicon oxide, quantum dots, gold nanoparticles. So it's all about combining different elements or different atoms to make nanomaterials. So it's everything just made with atoms. When variation of this arrangement of the atoms distinguishes the cheap from cherished, like a gold nanoparticle from a gold salt, or a quantum dot with good fluorescent properties from just basic atoms, and SiO2 making into nanoparticle from the basic sand-like materials. So I always go with a good quote, like our ability to arrange atoms lies at the foundation of the new nanotechnology. Like if we can arrange the atoms in a methodology in which we desire, then a new technology can arise. So variation of arrangement of atoms at nanometer scale is the foundation of nanotechnology. So believing in this principle and with a lot of learnings, in the last 4 years of my research career, I have fabricated various fascinating nanomaterials, which I'm showing here, like some magnetic fluorescent quantum dots, which have some both magnetic properties, fluorescent properties, then some graphene quantum dots with various elemental doping, then some polymers which are conducting, which have the conducting abilities, then several gold, silver nanoparticles, then different metal oxides, spinal metal oxides with various morphologies, then the graphene, which is the invention of the last decade, then V2O5 nanosheets. These are some of the few of the materials which I have fabricated in my research careers. Along with fabrication of the materials, we have done some beautiful functionalizations of the materials depending on the desire to desire or necessity of the application. Like what is the application needed, and the necessary modification of the nanomaterial or functionalization of the nanomaterial has been done. So this is a brief introduction and my achievement about nanomaterials, what I have been doing. Now, after synthesizing and functionalizing these nanomaterials, I have been applying these nanomaterials in several applications, like let's say from sensing to energy storage to drug delivery to imaging, several things. But today our topic is just limited to sensing. And limited to this sensing, I'm very fortunate to work with Professor Park in Shizuoka University, because we have been only focusing our work for the virus sensing. So this this virus sensing doesn't need any further introduction, because since last 1 year, even the layman understands very easily what is the importance of the virus sensing because of this COVID pandemic. Now, getting into the studies of virus sensing, brief introduction or history about virus sensing. RT-PCR, which is the gold standard for the virus sensing, which is even the technology used even today since several years, and the most reliable method, but having same advantages, disadvantages, like leads long time, very laborious, etc. But with the advent of nanotechnology, with the inventions in nanotechnology, we got several we developed several other technologies. Like among them, one of them is SIRS, which is surface enhanced Raman spectroscopy, which allows us to detect any biomolecules with necessary functionalizations of the nanomaterials, where sensitive and reliable sensing can be obtained. And some other methods which are recently developed are some rapid sensing technologies like lateral flow assay, which is majorly used for antigen or antibody detection. This is also one of the methods established during this COVID pandemic, but still people are relying only on RT-PCR because the reliability of this rapid testing is still not much. So every airport we want to enter, they need an RT-PCR negative certificate, even today. So further, with the progress of nanotechnology, several other methods have been established, are being developed, like fluorescence is one among them, which is a very well established, and a lot of research is being done with fluorescence methodologies. Then the fascinating properties of these nanomaterials help in the development of electrochemical methods, several electrochemical methods, starting from DPV, CV, impedance. Several methodologies can be developed for, again, the end of the day, the aim is developing a point of care testing virus sensor, or any kind of sensor. Along with this, calorimetry is also one of the most developed methods, wherein people use just determining the color. When there is a virus, the color changes. When there is no virus, the color doesn't change. But however, those several technologies are developing, every methodology is having its own drawbacks or advantages. Like there is a pros and cons for every methodology. That is why I think the reason why a reliable and sensitive sensor is not being developed for the point of care testings. That is the reason why we are still depending on the RT-PCR even today. So because now when I say that every methodology has its own advantage or disadvantages, so why not we combine 2 or 3 methodologies into one? Like we do only one kind of method. We follow one method which gives us both fluorescence signal, electrochemical signal, and calorimetric signal. Then my reliability is increasing. Then there is also some probability of increasing the sensitivity of the sensor. We try to develop some sensors in which we combine both electrochemical and fluorescence modality into one, or we combine both electrochemical and calorimetric modality into one. Like these both methods, one method which gives both electrochemical signal at the same time calorimetric signal. Like the virus, then further, if it is positive, then further do the quantitative analysis. These are some of the advantages when there is a probability to combine different methods. That is where I call it as dual modality. Instead of working with single detection methodology, combining several detection methodologies into one, where a reliability and high sensitivity can be obtained. Now, getting into this, to achieve this dual modality, or to achieve this combination of several methodologies into one, this is possible only with the advancement of the nanotechnologies, like preparing some hybrid nanomaterials. Like if we can develop some nanomaterials which have both properties, like different properties. Like here I say, fabrication of nanomaterials more than one functional constituent which act as a bifunctional markers is fascinating. So if we can develop some nanomaterials with 2 different properties, with two different properties which are necessary for the application, then this dual modality sensing could be possible. Like in and also in recently last 5 to 10 years, it has been established that separating the target analyte from the huge matrix will help in achieving high sensitivity, because this reduces the interference. So the sensing signal can be enhanced. There cannot be any possibility of interference when we do a magnetic separation. So now when we this is a very this is possible only with the advancement of the nanotechnology. Now separating these particles, that I mean the targets from the analyte, like let's say from serum, if we separate the virus using magnetic nanoparticles, so just separating is not enough. After we separate the same particle, if can do the signal enhancement, I mean the detection signal can be obtained from the same nanoparticle, then it would be very beautiful and very easy to develop a dual modality sensor, as explained here. So several people have tried to done like some previously, but for combining these magnetic materials with multifunctionality is an emerging class of materials which exhibiting some tremendous potential in advanced applications. As in, if you can see here, they combine, they try to encapsulate the magnetic nanoparticles and quantum rods into one polyester membrane. So inside the shell, inside a polyester shell, they try to encapsulate both the nanoparticles. So this shell had the properties of magnet as well as quantum dots. But however, there are some disadvantages, because magnet is in direct, there is some chance of direct contact, or there is a polymer shell. The fluorescence of the quantum dots can be reduced. At the same time, some other advancement of the methodology has been done, and they have tried to made a core shell kind of structure in which magnetic particles are inside, and they try to decorate with quantum dots and then coat a polymer shell for which helps for the functionalizations. But still, there is a direct contact. Now, if there can be any advancement, like if there can be any probability to create a particle in which the contact between magnetic particle and the quantum dot can be separated, but still they are existing in the same case. So the material would retain both fluorescence property at the same time the magnetic property. So we made a small try for this. So if you can see here, we have developed a sensor, a dual modality sensor for virus detection, wherein we have used the hollow iron shell outside in which the quantum dot is encapsulated, and there is some gap because of the hollow shell. There is some gap between the quantum dot and iron shell, so the energy transfer is not happening. So what we have done for the development of this method, this nanomaterial, is following the very simple molecular method of synthesis, like continuing synthesis. First, we have prepared the quantum dots with good fluorescence properties. Then iron nucleation has been done in organic. Then after the complete growth of the iron shell, as shown here, a controlled oxidation has been applied using the mixture of argon and oxygen gas. When the controlled oxidation has done, the complete shell of the iron has been oxidized and made a hollow shell wherein some gap could be achieved. Now, after designing this methodology, we have synthesized the material and done some sequential characterizations. As if you can see, this is the quantum dots, which are very small particles, around 8 to 10 nanometer in size, and then we have grown the iron shell on the surface. Like this depicts here. Here we can see the iron shell, which is grown on the surface of the quantum dot. We can see with the difference in the electron images. And then when the control oxidation has been achieved, we can see clearly there is some gap being created among the particles. And this is well established in the HRTM image, where some gap is obtained between the quantum dot and the hollow shell. So this explained the material which we were designed has been successfully synthesized. Now, coming to the properties, I wanted my material to have both magnetic property and fluorescence property, which is being established in this image. So when I place a magnet, all the magnetic particles are separated to edge, and under UV light, my material is still having good fluorescence. So this gave me confidence that the designed material has been successfully characterized. Now, have been successfully synthesized. Now, to further understand the various physicochemical properties, several further characterizations like XRD, magnetic moment, then XPS have been performed to understand the functional groups which are necessary for further functionalizations. Now, after successful synthesis of this nanomaterial, we have designed a strategy for the virus detection, that is the dual modality virus detection. So herein, what we have done is, initially the fabricated nanomaterial in which a quantum dot is there inside the hollow shell, we have attached antibody. We have conjugated antibody to this by covalent conjugation. the first process. In the second process, we have prepared an electrode on which we have got RGO, and we have again attached antibody for this. So these two were the precursor materials which are prepared before the sensing has been started. So coming to the sensing, the flow of the sensing methodology, first the virus solution, let's say the serum, the serum solution containing virus has been taken. Now our nanoparticles for which antibody was conjugated was dropped into this virus solution and allowed to incubate. So because of the specific antibody and virus interaction, the nanoparticles conjugated to the antibody and form a nanoconjugate. Now, after particular incubation time, the conjugation has been successful. We have placed an external magnet. So all the nanoparticles as well as the conjugated magnetic particles are separated, and then they are freshly dissolved into a new container. And now the prepared electrode, which further has the antibodies and RGO coated antibody conjugation is done, is dipped into the redispersed solution. So when this electrode is dipped into the virus solution, separated virus conjugate solution, the virus again further attaches to the antibodies on the electrode, making a sandwich-like structure. Now, when the electrode was removed out, when this electrode was separated from this, all the virus particles along with the conjugated quantum dots have been separated from the solutions. So this means the virus is attached to the surface of the electrode. At the same time, some nanoparticles, the synthesis nanoparticles are also separated from the solutions. And now, when this particle is separated, this virus is having RGO, so it is having very good conductivity. But when virus molecules are attached to this, virus particles are attached to this electrode, the conductivity of the electrode is decreasing because the charge transfer between the electrode and the electrolyte is restricted. Because a biological film is forming, the non-conducting biological film is forming on the surface of the electrode. So along using this, we have tracked upon increasing virus concentration, the impedance of the impedance values, the charge transfer resistance values of the electrode has been increased. So in this way, we could establish one kind of calibration curve, virus sensing. At the same time, when the electrode is removed, with respect to the virus concentration, the nanoparticles also were removed. That means the amount of nanoparticles in the remaining solution decreased. So the fluorescence intensity also has been decreased. So using this remaining solution, we further established a fluorescence modality. So herein, we have developed only one nanoparticle and only one methodology we are following. But at the end, we are getting two different signals in electrochemical modality as well as fluorescence modality. So we are establishing that two different modalities can be obtained, two different signals can be obtained to determine the virus. So the confidence can be clearly confirmed for the determining the amount of virus present in the sample. Now, after designing this successfully, we have optimized several parameters which are necessary for sensing, like the concentration of the nanoparticles, antibodies, everything. After successful optimizations, we have done the virus sensing. As in here, you can see when the concentration of a virus is increasing from 10 femtogram to 10 nanogram, the charge transfer resistance of the RGO, antibody-coated RGO electrode consistently increased. So wherein we could establish a linear calibration curve from 10 femtogram to 10 nanogram. So the good calibration was established. At the same time, we have also monitored the fluorescence of the remaining solutions. And as the virus particles were increasing, the fluorescence consistently decreased, where we could further establish a calibration. Like if a particular sample is having, let's say, 1 nanogram, we could get this signal at the same time, this signal. So we are getting two different signals for one particular concentration. So in this way, the developed sensor is, we could establish what we have thought is been established. But however, reliability is still a question. So we need a comparison. How to say our method is very good. So for this, what we have done is, we have infected a monkey with virus, and the fecus of the monkey was collected from 0 to 45 days at particular intervals. Now this fecus has the virus particles, which were estimated, the copy number of the virus particles was estimated using the gold standard RT-PCR. So we can see from day 5 to day 45, the RT-PCR, the green color RT-PCR data, the copy numbers days, and they were stable until few days, and the copy numbers decreased. So this was the pattern shown by the RT-PCR data. At the same time, when the same fecal samples were used to detect the virus in our developed in-house developed methodology. So wherein we can see both signals. We got both signals. One is from fluorescence, the blue color, and one is for electrochemical impedance, that is red color. So the signals which are obtained from these two methods also followed the similar pattern with the RT-PCR data. That means our developed method is in collaboration with the data obtained from the RT-PCR methodology. So wherein it gave us very confidence, yes, we are attaining we are attaining good reliability and sensitivity, and we are even comparable with the gold standard RT-PCR. So now, after developing this work, we still thought the developed dual modality strategy helped to give more reliability. Then we thought, how can the more sensitivity be achieved? How more sensitivity, that means detection limit can be even down. We have, for this, we have developed another methodology, still sticking to the dual modality principle. So in this methodology, what we have done is we have choose the V2O5 nanoparticles, the vanadium pentoxide nanoparticles, because these nanoparticles have both can exhibit some signal in both electrochemical as well as optical methodologies. So what we have done is, after synthesizing these nanoparticles, we have encapsulated them inside the liposomes. So so that one liposome particle is having a lot of several hundreds of particles inside. So they are encapsulated inside the liposomes, where signal amplification can be obtained. And then after the encapsulation was successful, we functionalized our liposomes with antibody of interest, like whichever virus was detected. So in this case, we detected norovirus. Then after the functionalization of liposomes encapsulated V2O5 with the antibodies, similarly, magnetic nanoparticles were functionalized with antibody, and these two particles were dissolved into the virus solution. So this is a virus solution along with liposomes and magnetic nanoparticles, and they were incubated them for a few times, and then so here what happened is the magnetic nanoparticles as well as the liposomes attach it to the virus particles, and they form a sandwich-like structure. Then we have used a magnetic separation in which all the magnetic nanoparticles along with virus and the conjugated liposomes were separated. And this separated mixture was mixed with Triton X to break the liposomes, so that all the encapsulated V2O5 nanoparticles can be released. Now, these released V2O5 nanoparticles generated two kinds of signals. Like they were, when used in the electrochemical modality, they could generate some DPV signal. At the same time, when used in optical modality, they were used in TMB oxidation, like in the presence of H2O. So two-way detection was possible using this methodology. So now getting into, so again, similarly, we have successfully characterized the material, optimized all the conditions necessary for the detection. After the optimization has been completed, then we have gone to the detection. So here, if you will see, this shows the DPV curves, wherein the DPV signal increases when the virus concentration is increasing. At the same time, the optical signal is increasing when the virus concentration is increasing. So when more virus, more liposomes are coming, so the amount of V2O5 is increasing. So the rapid oxidation, the rapid TMB catalysis is happening in this principle. So, but however, in calorimeter, because sensitivity difference, we could extend our linear calibration. Like in the previous case, both calibrations were in the same range, in the same particular range. But in this particular methodology, we observed that the calibration line could be extended. Like being electrochemical, being more sensitive, we can detect until 10 femtogram level, as in here. But optical modality, we can go until 100 nanogram level. So this stretching of the wide linear range could be obtained using the developed methodology. So along with these methodologies, we are recently even trying to develop few other methodologies as well, still following the dual modality principle, where two signals can be obtained, either electrochemical and optical, or combination of others, which can be used for sensing. So coming to the conclusion, so we followed a new strategy for the fabrication of magnetofluorescent nanoparticles designed for virus sensing, and the gap which is obtained between these quantum dots and iron oxide maintains the fluorescence with minimum quenching effect for the quantum dots. In addition, the quantum dots were protected by the shell. So the decrease in the fluorescence was, the quantum dots were not at all affected by the external matrix. This was the further advantage of this methodology. In the same time, we employed liposomes for the V2O5 nanoparticle encapsulations, which we established several calorimetric, fluorescence, electrochemical readout, virus sensing, where dual modality has been still adopted. At the same time, there is a possibility for replacing the TMB in the calorimetric method with some fluorescence method, where a good alternative for future study can be done. At the same time, some additional technologies, the rapidly progressing technologies like OER, HER, using the water splitting, these kind of, because the signal generated in these kind of technologies is very sensitive, and also they can be self-powered. If we can bring these technologies into for developing sensors, so it can be very advantageous to do on-site detection, where even in some countries where even the power source is not available. When we bring these technologies into virus sensing, we can use the on-site energy generation. At the same time, we can also perform the virus sensing. And finally, I would like to thank all my lab mates, and my sincere thanks to JSPS for providing me the fellowship and allowing me to come to Japan and pursue this excellent research. Thank you.
Thanks so much for good presentation. Now we have time to ask some questions. Anybody welcome to ask questions? Hopefully from student part.
I have a question. Yeah, um, it's very excellent work. I wonder, you used the gold electrode, right?
Yes.
Yeah. Then you immobilize the graphene on the gold electrode.
Yes. Reduced graphene oxide.
Yeah. So can you explain the reason why you use don't use the gold electrode directly to measure
Okay, so when the first thing is, we need some kind of matrix to attach antibody. Okay, definitely on gold electrode directly there is a possibility of attaching antibody, but when we are using some kind of nanomaterials, the surface area of the surface area is increasing, so that there is a high possibility of high loading of antibody, and high loading of antibody is very essential to make a broad sensor, to increase the linear range of the sensor. At the same time, this will help for characterizing the the impedance. Yeah, so these were the reasons for using reduced graphene oxide instead of using a bare electrode.
Okay, thank you. Another question.
Yes.
You use the virus. So I don't know what kind of virus you use in your lab. Is any protect technician when you use the virus?
Okay, so actually, the work which I'm demonstrating here, we have developed for a hepatitis E virus. But initially, what we do is we don't work with the real virus. We do all the optimizations and calibration studies using virus-like particles. So these particles are just the capsid of the virus without the nucleic acid. So these are prepared in the laboratory. We use this initially. Then after optimizing the whole sensing process, then we use some deactivated virus samples for checking the reliability of the sensor.
Have you tried your technique to measure the COVID-19 virus?
Yes, we are in the process of doing that. We just received some COVID deactivated viruses, and we are in the process of developing measuring for COVID virus.
Okay, thank you. Very good work.
Thank you very much, ma'am.
Any other question from Korean side or any other side?
Okay, I have a question. Yeah. Look the page 11. Page 11. Yeah.
Sorry, before this. Okay, here.
So I want to know, did the shells influence the quantum dot efficiency?
Sorry, can you please repeat?
I want to know the shells influence the quantum dot efficiency.
You mean the shell or the size?
The cells.
Yes, exactly. When the grown. Like in this particle, particle, when the shell was completely grown on the quantum dot, the fluorescence was almost quenched. The quantum dot did not show any fluorescence. But when we made it hollow, the fluorescence was reobtained. So here we predicted that because the creation of the gap, there is a chance the fluorescence was coming back. So shell has a very importance, and also we tried to maintain the thickness of the shell. We tried to control the thickness of the shell. Varying the thickness, also the fluorescence was optimized. We have also performed those experiments. Sorry, I didn't included those optimization status today in the presentation.
Okay, now almost time's up. We have just one more question left. Any other guy from any side?
Oh, can I ask a question?
Please.
Comparing with the CD quantum dot, when you coat the hollow shell, how much the quantum yield decreased or changed?
Oh, so initially the quantum yield was there was no after I'm coating the iron shell, there was no fluorescence at all. So we did not measure the quantum yield, but here still 14% of the quantum yield was maintained from the original.
14.
14, 1-4.
Okay, thank you.
Yeah. Thanks so much. Once again, thank you for
Thank you very much, Professor.
nice talk, Dr. California. And the second talker from Chinese part, Shanghai University, Ji Mao, and he's talking about the design and synthesis of MOF with synergetic antibacterial activity. So when you're ready, you can start.
Okay, now I'll begin my sharing. Okay, I'll begin my sharing. Dear experts and professors, I'm a doctoral student of grade 20 in Shanghai University. It's a pleasure to be here and an honor to present my recent work about the antibacterial effect of MOF-based composed biomaterials. I would like to concentrate on the synthesis and characterization of materials. That is my sharing. I think it would be better to start out by looking at a pie chart. The statistic distribution of microorganisms involved in the statistic of human infection. Among the gram-positive bacteria are the most important infection microorganism. Of course, gram-positive infection is also common in surgical suppurative infection. The antibacterial mechanism of antibacterial material is no single, which is caused by a variety of damages. See in this picture, such as inhibition of cell respiration, production of reactive oxygen species resulting in DNA strand breakage, and so on. What is shown in the pie chart is published scientific papers on the antimicrobial materials and coatings, antimicrobial polymers, titanium dioxide-based antimicrobial materials, and copper-based materials, and silver-based materials.
Yeah, the format should be changed. The slide is too small to see. Check presentation type. Yeah, okay, perfect.
Okay. So I'll try again. Okay. I think it would be better to start out by looking at a pie chart. So I
Like
start at the page 2. Okay. The page 2 is the statistic distribution of microorganisms involved in the statistic of a human implant infection. Among them, the gram-positive bacteria are the most important infection microorganism. Of course, gram-positive bacterial infection is also common in surgical suppurative infection. The antibacterial mechanism of antibacterial materials is a new single, which is caused by a variety of damage, such as the inhibition of cell respiration, production of reactive oxygen special generation, resulting in DNA fragment or condensation. Uh, the antibacterial mechanism is so complex. What is shown in the pie chart is published scientific papers on the A. The fig A is the antimicrobial materials and coatings. Fig B is the antimicrobial polymers, and fig C is titanium dioxide. D is copper-based materials, and E is silver-based materials. Therefore, the key and what we can see in this figure in 2020, everyone's work has extended for a period of time. So the key is to find effective antibacterial materials. Compared with the traditional antibacterials, nanomaterials do not cause bacterial resistance due to their multimode antibacterial effect. MOF is a kind of multifunctional nanomaterials. It is a kind of purpose coordination polymer formed by organic linkers and metal ions or clusters. The internal structure and the surface physical chemistry properties of a morph can be controlled by the selection of organic linkers, metal ions, or clusters. In addition, the size and the shape of a morph cluster can be reasonably adjusted by the selection of temperature, solvent, and reaction time in the synthesis process. And silver containing compounds uh, like inorganic silver cells and silver complex have excellent broad spectrum antibacterial activity. The antibacterial activity is related to the slow release of silver ions from silver-based nanomaterials. Despite their extensive usage and benefits, the nanostruct silver particles can't be fully exploited due to less stability and rapid aggregation as it seemingly constrains antibacterial efficiency of silver nanomaterials in some practical application. Using morph as a template to embolize silver nanoparticles is an effective method to slow the inherent shortcoming of silver nanoparticles in antibacterial application. For silver nanoparticles, morph can make it have a high activity thanks to the high porosity and large specific surface area of morph. On the other hand, morph has certain antibacterial activity, which can form a good synergistic antibacterial effect with its loaded silver nanoparticles and improve the antibacterial ability of the compost. In this work, we synthesize a new silver-containing antibacterial agent based on copper morph. The AMTA selected as a bridging ligand exists in nitrogen carbon double bond and sulfhydryl groups and ammonia. The AMTA has 5 potential coordination sites. ADO compounds are found to possess extensive implementation in various biological applications. So AMTA is an ideal bridging ligand. Nano copper morph was synthesized by hydrothermal method achieved silver nanoparticles uniformly loaded by in situ reduction of silver nanoparticles on the surface of morph. The isonacist morph possesses a sphere morphology with a uniform but controllable size, as referred by the was shown in fig A and fig B. The diameter of a copper morph is 500 to 800 nanometers. The EDI spectral date of copper morph sliver is shown in fig A. Due to the low content of silver, the peak of silver is not very obvious. The element composition can also be seen from the table below. The loading of silver nanoparticles into the copper morph nanoparticles is confirmed by comparison of the PSRD patterns of bridging ligand, copper morph, and copper morph silver, which was shown in fig A. The copper morph exhibits salutation diffraction peaks in agreement with the previous report PSRD patterns. While the copper morph silver nanoparticles also have the characteristics of copper morph and other newly peaks. Peaks at 2°44 4, which can be respectively attributed to the 200 and 220 lattice plane of silver nanoparticles. This observation demonstrated the reduction of silver ions and the loading of silver nanoparticles. The FTIR spectra of AMTA and copper morph and copper morph silver are shown in fig B. For pure copper morph, different band assigned to different ligand. The FTIR spectra of the copper morph silver nanoparticles did not show a significant difference from the spectra of copper morph. To get the direct evidence of the existence of silver in morph, we observed the existence of silver nanoparticles by TM. At high magnifications, we can see the silver nanoparticles as shown by the right circle in the fig B and fig C. Due to the three-dimensional structure of morph, we can see a wealth of silver nanoparticles at its edge, with the particle size about 3 nanometers. In addition, at high magnifications, we also verified the crystallinity of morph and the gold crystallinity of morph can be characterized by the lattice fringes of pattern and the electron diffraction of fig B. Also, the element distribution under TM is uniform. Like by my we didn't finish it now, so it need to be some time to test it.
Okay,
we think it have also
okay.
we think it have a high.
Oh, go ahead.
Keep going on. Yeah.
Go ahead. Okay. What I want to know is what kind of species of bacteria? Gram positive, gram negative, very many kind of bacteria. Specifically,
we think this compost have like the gram positive.
Yes. Gram positive. Name of the bacteria name? Too many bacteria in gram positive.
Yeah, right. Yeah.
Okay, it's okay. I know gram positive bacteria you're targeting now. Okay. Okay.
A bit difficult
Thank you.
question, I believe. Any other question from audience? I mean,
I would like
just
to
from
ask a
student
question.
part, yeah.
So you have
To
prepared, you have
increase it.
synthesized this MOF particles, right? So I would like to know,
Yes.
have you checked any effect of the solvents on the synthesis of your MOF, based, I mean the morphology, and also did you try to do the surface area analysis for your MOF? Because I think that is very important in your application part.
In the we selected the DMF as a
Okay.
solvent.
Okay.
DMF.
Okay. And any particular reason you selected only DMF? Why you are not using any others like methanol or ethanol? Any particular reason for only using DMF?
In some in some tests we use the we use other solvent, but it's not good compared with the DMF. So we selected the DMF as a solvent. It can be make the compost more severe and uniform in the test about compared with another solvent. So we think DMF is a good solvent.
Okay. And how about the surface area? How much was the surface area?
This question we don't. Can you repeat it?
How much was the surface area of your material, the end product? Did you analyze the surface area?
Did you analyze what something area? Well, we didn't hear the exact between the analyze and areas because of the technical problem. Can you ask just the question again?
I would like to know how much was the surface area of your prepared nanomaterial.
We don't make this test.
Okay.
You didn't
yes,
explain yet. Okay.
Okay. Thank you very much.
That's very good. Okay. Any other question? We still have plenty of time.
I have a question. When you make this mop, how do you put the silver nanoparticles in the mop?
No, it's a gas special, not it's just a picture, not the real model.
I see. So you didn't characterize
It's
it
just
yet.
a kill. It's just a kill.
I see. Yeah, I see. Now we have just time to ask us just a short question. Any other guy? Just challenging from student part. Don't hide. This is just the informal meeting. Don't worry about your. Just ask through the chatting. There are several types of MOFs. What MOF did you use? And is there any special reason for that? That's the question from the Young Che. Do you have answer?
Yeah, the metal ions couple have a good antibacterial. It has the synergetic antibacterial effect. So the AMTA have a it's a good ligand. We select it because it possesses a good antibacterial effects
Okay.
in some research. So we think the linker and the metal ions have the synergetic effect on the antimicrobials.
Okay, thanks so much. Once again, we appreciate Julie Mao's great dedication. Thanks so much. And next presenter is Ju-Yong Kwak in CNU, Chungnam National University, and he's talking about the helical magnetic field induced chiral plasmonic sensing. Let's hear about his talk. Yes, yeah, now it's clear.
When it first on sale, there were no side effects in various animal tests, so it was sold under the miracle drugs, and it was easily available at pharmacies. However, pregnant women began to born deformed babies. So what is the reason? Whether the cause was the revealed to be chiral structure that physically activated differently in human. So what is the chiral? The hands are perhaps the most universally recognized example of chirality. The left hand is non-superimposable mirror image of the right hand. No matter how the two hands are oriented, it is impossible to coincide across all axes. Drug and amino acid can form chiral in the process of synthesis, and they can be beneficial or toxic to humans. The problem is that even very small amount of this chiral can be fatal to the human bodies. Currently, the global pharmaceutical market is expected to expand to the scale of up to about $442 billion, and the important fact is that about 70% of new drugs are chiral. Therefore, it's necessary to develop qualitative or quantitative analysis technology for chiral. In other words, it is very important to develop an analysis technology that detects the chirality in very low concentration. So how can check the chirality? The chirality could be checked by some equipment like circular dichroism, HPLC, and NMR. Among these, the circular dichroism is very quick method that has more high limit of detection, I mean the LOD, and it is also cheap in terms of the cost. So CD is often used for chirality analysis. CD is data by difference in observance between the left circular fluid light and right circular fluid light. If the sample is chiral, the CD spectrum was seen oppositely each other. As a result, it is possible to check whether the sample is chiral or not. However, this circular dichroism has a severe limitation. For example, in the case of the amino acid, it is very difficult to detect what kind of amino acid because of a very similar CD spectrum wavelength. The plasmonic material can be used for enhancing or detect chiral signal. The plasmonic particle has specific optical property. When they contact with the light at a specific thickness or size, they form oscillating the electronic cloud. When two or more plasmonic particles approach each other, the resonance of individual particles start to hybrid. As a result, a strong enhancement of a local electromagnetic field occurs around the metal nanostructure. This plasmonic enhancement can be used for source and CD to analyze chirality. But there are still several limitations. It enables to the detection of few amino acids, and currently most of the paper available enhance the L or D form. Second, I mean it is also impossible to analyze different amino acids each other. But other type of the amino acid, LOD has just 10 micromole. As follow, in order to increase the sensitivity of plasmonic enhancement, the plasmonic nanoparticle is alignment chiral. The plasmonic, if the plasmonic nanoparticle is chiral, the plasmonic nanoparticle have also chiral property, which can react very sensitively to other chiral materials. So they can react differently depending to the structure of chiral material. At this time, template is required. The template, such as the DNA, peptide, and cellulose, is used for the chiral arrangement of plasmonic nanoparticles. However, the template makes it difficult to tunable the arrangement of nanoparticles. So structure change may be delayed because the particles were fixed from the template. But structure change is very important because the enhancement of chiral like amino acid differently measured depending on the chiral structure of plasmon. Therefore, it's necessary to change the structure very quickly and accurately. The helical magnetic field can overcome most of the mentioned. This is magnetic plasmonic nanoparticles exercise in our laboratory. This magnetic plasmonic nanoparticle can be aligned, follow the magnetic flux, and it is possible to make a chiral structure by adjusting the angle of two magnets. For example, if the angle is 45, it makes a left-handed structure, and it makes a left-handed CD spectrum. And if the angle is 135, it makes a right-handed structure, so it makes a right-handed spectrum. The highest characteristic property angle is 45 and 135. So what happened? So I fixed the angle to 45 and 135 for left-handed and right-handed. And also, the helical magnetic field is not required a template. In addition, by adding another chiral material like amino acid into this alignment, the specific peak wavelength will be shifted. through the interaction between the amino acid and nanoparticle chain. This is a helical magnetic field generator in our lab. If the adjust the distance of the two magnets, the magnetic strength can be changed, so the characteristic property could be changed because high the magnetic strength means many magnetic flux. It means the alignment chain is high. So if the distance of this magnet is too close, the strength is also strong, so it's very hard to form the chain for a long time. However, if the strength is too low, the series intensity is also low. Therefore, the distance between the magnets was fixed at 3.6 centimeters. The following is the series spectrum of amino acid without a helical magnetic field. It is impossible to determine what kind of amino acid in this spectrum. However, for amino acid, the structure is different each other. So in the helical magnetic field with magnetic plasma nanoparticles, it is possible to identify what is cysteine or glutamic acid through the different wavelengths as follows. This is LOD of the cysteine. In this spectrum, we can't detect chirality in 10 nanomole. However, by using the helical magnetic field with magnetic plasma nanoparticles, the chirality of the cysteine can be detected in around the 700 nanowavelengths. I mean, at the left-handed, this cysteine has higher characteristic property than L-form, but at the right-handed, the L-cysteine has a higher characteristic property than D-form. So using this different characteristic property, the chirality can detect, what is L-form and what is D-form. And the chirality of polymer also could be detected. The polymer also has different characteristic property, so it's possible to distinguish between the L-form or D-form. Actually, the amino acid oligomer polymer differ in size. It means that impossible to different interaction with a nano chain in helical magnetic field. As a result, the smaller the size, the lower the characteristic property. The lower the characteristic property affect depending on the concentration. Using this chiral molecule, oligomer and polymer can be distinguished from the helical magnetic field. Stop.
Oh, it's very slow.
Very slow. By using the helical magnetic field, it was possible to very easily distinguish chiral amino acid at 100 times lower concentration. In addition, the oligomer and polymer also can be detected. In other words, the helical magnetic field is powerful knowledge that not only overcome the disadvantage of the previous technology, but also detect the variety materials. Thank you for listening.
Thank you for good presentation. It's time to ask some questions. I just encouraging students
May,
to
may
ask
I,
questions.
may I ask questions?
Any silly question would be acceptable.
Hello?
Okay, hello.
Hello? Can I ask questions?
Yes, we can.
My name is Indra.
Hi, Indra.
Yes, I want to ask about the detection of the amino acid chirality. So, I want to ask some simple question like the in plasmonic, I know is there's some kind of important factor of the distance between the analyte and also, so let's say some analyte and also this the structure. So in here, so the amino acid have contact with the nanomaterials, or is there any distance dependent for the chirality of the value of the chirality, the contact? Thank you.
So you want principle of the yes?
Yeah, I mean,
spectrum?
if I mean, is there any study about the chirality detections of the amino acids based on the distance? Is it possible to investigate the distance dependent of the chirality?
The first question is the nanoparticle make contact with the amino acid. 나노파리클이 아미노 액시드하고 실제로 결합을 하는지 뭐 이런.
Actually, in the answer is I already checked the size, but I can't find the contact. I mean the aggregation with the amino acid and nanoparticles. Almost same. Yeah.
So there's not distance dependent, we can say.
Not about the
dependent,
but the wait. Stop it. The presentation. I checked the simulation and the interparticle, but it's very similar to the result of my experiment. So I think it's when the added the amino acid, is the interparticle distance is changing. So
interparticle distance is not changing depending on the amino acid. That's your answer.
Okay, thank you for the answer.
Okay, thanks so much. Any other questions?
I would like to ask a question. So first of all, it was very nice talk, John. Thank you very much. So in the slide number 13, you showed an instrument in which you are measuring this magnetic moment. Can you go to slide number 13, please?
Magnetic moment?
Yes. So the instrument, yes, the instrument which you are showing here to measure in which where a magnetic and motors are placed, is it an in-house made instrument or it is any commercial instrument?
How to make it? How did you make it?
Sorry, I can't understand.
Oh, sorry. I want to just ask, this instrument, did you develop this instrument in your lab or did you order it from some company?
Yes, company. We order and we design. And, yes.
Okay. I'm completely unaware. Okay, thank you. And another one small question. I just want to know, is there any effect? Like if I see the particle size of your nanoparticles, they are around 100 nanometer. Like if we can make the nanoparticles little small, would there be any effect on your detection parameter?
Side effect.
Okay. Yes, right. In the spectrum, the spectrum is affect the nanoparticles. I mean the core size, because because this spectrum is from the plasmonic resonance. So if the shell size is different, it means the core interdistance is changed. So it's change the wavelength shift.
Yeah, right. There must have a side effect because of this is the plasmonic mode. So
still there is any time? Can I listen?
Yes, please ask some question.
Okay,
Yeah.
I am from Shizuoka University. Just a normal question. Like in your method, you can maybe detect the L16 or the
Ours, yeah,
RC,
this
right?
system.
Right,
Yeah.
right.
So you can detect this one, right? Like L and D, right? System.
Uh,
So I mean, it's nice, it's good, but I just want to ask one small thing. Like L16 is a very common. We have this one. So what is the significance to detect the D system?
So
sorry, I can't. So you mean
I
the?
mean, yeah, definitely there is some amino
I can
acid.
translate it. I can translate it. 주용 씨, 이 장비를 이용해서 다른 것도 모니터링 할 수 있냐 물어보는 거예요.
Yes, of course, of course. The L system and this system, and wait, I already checked the different amino acid. For amino acid, we can detect the differently wavelengths. So what? So we
No,
can.
I can understand that you can detect, but I am asking
Yeah.
that only the L16 is a common for our body or everywhere, but not the D. Then why? I mean, why you are trying to focus on to distinguish between these? Not, I am not asking about
왜
your.
LCC를 모니터링을 했을까? 네.
Why?
Now it's so.
Yeah,
Why?
this is some introductory question.
Yeah.
Yes.
First, the system is the affect the human. For example, the brain affect the air system. So I first I check the air system and this system.
We just want to know the physical parameter first, then we are going to make some meanings later about the biology or any other environmental issues. So that's
it's okay, sir. It's okay. Okay. So, however, I mean, your concept is very nice. I mean, the method of detection of the CD is also very nice. Thank you for your presentation. It's nice.
Once again, we thank you, Juyong, for good presentation. Now it's the intermission time, so till 10:30 we take a rest. Thank you for first session. 커피 한잔 먹으러 가야겠다.
Yeah, that's all. It's okay. Yeah, all right.
Progression is good. Answer is good.
Yeah, it's okay. Like the pronunciation is a little bit hard to hear. That's fine.
Really?
Oh no, that guy. All right.
I added one TM image. 이거지. 컴퓨터. 반대로.
오후야.
네, 4시.
오케이.
한번 켜볼게요. 혹시 잘못하면. 아, 네네.
아, 힘들어.
Hello, Professor.
My voice.
Yes, is it clear, my voice?
Oh, yeah. Very clear.
Yeah. Is it called?
Oh, Zoom technology is very good. Yeah, we'd better do this kind of conference frequently. Because we cannot go to Japan, China. It's impossible till
Yes.
this.
And in Japan now also, in Japan
Yeah.
now increasing again the coronavirus.
Getting serious.
Yes.
Korea also quite serious at the moment.
Yes.
Now the university are almost closed.
Oh, in Korea still closed, the university?
Yeah. So we do online class only.
Class.
Yeah.
Oh.
So there are no students on the campus.
We also did online class sometimes.
Yeah, right.
Not always, yes.
Yeah. It's strangely, nowadays I'm missing a student.
Yeah, Professor missing the interaction. You miss the interaction with the student.
Yeah, so now there is no interaction with the student. Only through the online.
How about in the lab, Professor? I mean, like in
Lab
the.
is working. Yeah, lab is.
working.
Lab is exceptional place. So yeah,
It's not possible to do online like in the lab.
Impossible. There are a few students doing online. I mean, some simulation guys are doing the online. Yeah. Otherwise, how to pipette by online?
By online. Virtually pipette. Pipette.
Yeah, right. We need avatar. Now there are so many new students in Shizuoka nowadays.
Yeah. In our lab itself, we have so many new students, like 6.
Yeah. Right.
7.
Yeah.
Yes.
Hopefully.
Even in our group, we have 3 new students. 3.
Oh my goodness.
Yes. So more manpower.
Perfect. Okay, so it's almost time to have second session. Chen, are you ready to do it? Please turn on the audio.
Okay. Sorry.
Yeah, Shanghai looks like summer.
My room is summer. Outside is winter.
Oh my goodness. Korea is very cold today.
Yeah. Okay. Let's start our second session. The next speaker is from the Shizuoka University. The speaker is Indra Memdi Chris. Please.
Thank you. I will start. Thank you for the introductions. I would like to share the screen.
Yeah.
Yes.
Okay. Okay. Can I start my talk? I will start the talk. Good mornings, everyone. Today I would like to present our work in biosensing, especially in the colorimetric detections. When we talk about colorimetric detections, it means that we are the detection signals come from the development color in the biosensor or in the sensing systems. So based on the current developments, we can detect the presence of the virus in the samples. In addition, introduce a nano carrier to bring in the substrate or the signal molecules in the biosensor. So, as we know about virus, because of the coronavirus infectious outbreak, I think I want to highlight more about how we can detect the virus using the biosensor. Now, majorly there's two biomarkers that we can use. First is the antigen, which is mostly on the surface of the virus, although it's not always on the surface, such as nucleocapsid proteins, which is located inner side of the virus. So mostly on the surface we can detect directly, but when we're talking about the proteins or nucleic acids inside the virus, we need to have a pretreatment to lysis the cells and extract the insides of inside the antigen or the nucleic acid for detections. And for the performance of analytical performance of the biosensor, we mostly see two major things. First is the sensitivity, which means that how the performance of the biosensor can detect the virus as low concentration as possible, or the selectivity, which mostly come from the specific moieties such as antibody or aptamer that can detect the specific virus and distinguish it from other viruses. Um, as described previously about the substrate molecules, in this case we are using biosensor with enzyme and substrate relationship. So in a general approach, the in the detection of biosensor, we detect the viruses by the capture moieties will capture the viruses, and when we introduce our probes, it will bind to the binded virus. So it's dependent on our probe that binded on the virus, and we introduce the substrates. As the probe is nanoenzymes, it can catalyze oxidize the substrate, and based on the substrate color change, we can determine the presence of the viruses. So by the presence of the enzyme and substrate in a systems, we can generate the signal to introduce the we can determine the virus in the sample. So speaking, so how about if I switch between the subset and the enzyme roles? How about now it's dependent on the subset, not dependent on the amount of the enzymes. So I as the substrate catalytic oxidizer is equivalent to the presence of the virus. By introducing this TMB, tetramethylbenzene, which is a chromogens, which is our signal molecules, in the system, we need abundance of it. So first we make it a collective amount of the TMB in a collective amount, then we encapsulate it for a further abundance of TMB in a single individual's binding with the virus. First, we co-precipitate the TMB with BSA, a bovine serum albumin, as a protein stabilizer, forming TMB nanoparticles. Then we encapsulate the TMB nanoparticles inside the PLGA or PVA, forming encapsulations polymeric nanoparticles with TMB nanoparticles inside to make it more abundant. Then for the nanoenzyme, we also use nanoprecipitation to form a copper nanoflower using copper phosphate as the backbone and BSA as the stabilizer. So TMB nanoparticles and TMB nanoparticles in PLJ shows a similar visualizations, as TMB is dissolved in DMSO but not in water, and BSA is dissolved in water. When we make a TMB nanoparticles, when we know nanoprecipitated, we can show some cloudy solutions. Is dispersed in water, and also TMB nanoparticles in PLG also show similar cloudy visualizations, showing that there's no change in the visualizations analysis on these two nanomaterials. And based on the TM image, we can see the increase of size when TMB nanoparticles is around 40 to 50 nanometer. But when we encapsulate it in the we encapsulate in the TMB nanopart in the PLGA in the polymeric boundaries, we can see agglomerate-like structure, but we can see clearly that it was within a boundary. So based on this TM image, we conclude that we can encapsulate the TMB nanoparticles in the polymeric nanovesicles. Going through the nanocouple nanoflower as a nanoenzyme as is a relationship between both of them. So nanoenzymes, we prepare with nanoprecipitates and we can see a size around 500 nanometer, and we assay this couple nanoflower depending on the TMB, our chromogen. It shows an increase of velocity, which means that there's a dependent of the TMB amount for the catalytic activity of the couple nanoflower, showing our both system can be adopted for our biosensor. But however, when we apply the biosensor, the non-polymer nanoparticles into the biosensor, we need to also lysis the chromogen, so it can be also utilized as the signal molecules. First, as we already encapsulate it in the polymer nanomaterials, we need to lysis the polymer, and after that, the TMB nanoparticle will come out, and we dissolve the TMB nanoparticles, and because of the presence of the hydrogen peroxide and also nanoenzyme, it can show color change. So we use DMSO to lysis the polymeric, but in the same time, it's also help to dissolve the TMB nanoparticles into TMB molecules, and is abundant because of our approach of the nanocarrier. Then only in the presence of this all component, hydrogen peroxide, nanoenzymes, DMSO, and also our TMB nanoparticles, it can show color change. So this is our detection scheme. So in the A is a general approach. So we capture the virus using the capture moieties, which is antibody. Then by introducing our TMB nanoparticles PLGA, it shows immunosandwich structure formations. Then by DMSO, we lysis the polymer, and in the end, it also catalytic oxidize the TMB using copper nanoflower that we introduced last, and so the color change to detect the presence of the virus in the samples. Moving forward to our detections, so we detect three viruses. First is influenza virus, which shows a good calibration. So there's a function of absorbance depending on the concentration of the viruses because of the binding of the immunosandwich. Then also there's also the interference effect, which is we can neglect from the detections. So it's specific because of the antibody on the nanomaterials. Then after that, we also detect SARS-CoV-S proteins and norovirus particles, which different antibody. So it also can detect the detection based depending on the concentration of the virus. At last, we have introduced the nanocarrier of TMB in these systems with DMSO as the lysis molecules for these nanomaterials. And last, we can detect sub-femtogram levels of the virus using our biosensor. Thank you for the attention.
Yes, thank you for your presentation. Any question? No question? Junjie.
Question?
Yeah, I have a question. Your work is very great. I have a question about whether the synthesis, the nanoparticles, stability of such as changes in size over time.
Oh, okay. Okay. Thank you for the questions. Is it Mr. Kwak? Mr. Juyong? Okay. Sorry. Thank you for the questions. As we also check the stability of our biosensor. Actually, we didn't check the morphology, but we only check the performance of our nanomaterials in the biosensor. It actually shows a decrease in several weeks because of two things. Because of the antibody itself, and also one again is actually, I think, because of the stability of the nanomaterials. We expect that because it was our nanomaterials or polymeric nanomaterials, it can be degraded also in the aqueous form, but it takes around 1 month less. So for the stability of the nanomaterial is okay, but we didn't check the change of the size. That's actually we missed that part. We didn't check the size, but we only check the stability, which is around 1 week for 2 weeks for the biosensor, but for the materials itself is around less than 1 month.
Okay, thanks for your answer.
Thank you.
Okay, another question.
I would like to ask a question. So, is it when you are encapsulating your chromogen molecule, what would be the advantage if you are encapsulating your nanozyme?
Can I repeat one more?
I said you have encapsulated the chromogen, you have aggregated the chromogen inside this polymer. But what would be the advantage if you are encapsulating the nanozyme instead of your chromogen?
So thank you for the questions. So basically, before this work, we also have published another work. Silencer, it's double. Basically, we already published another work, which is of course your work, which is platinum Phyto05, which is nanoenzyme which encapsulated in the liposomes, and also we also have another works previously with the fluorescence encapsulations. But for the encapsulation of the fluorescence, we saw not really strong sensitivity because of the it's possible of the aggregation of the fluorescence itself. But for the nanoenzyme, I agree that nanoenzyme is quite good and also it's very interesting to be encapsulated. But the advantage of our chromogens compared to nanoenzyme encapsulation is that as its chromogen is a signal molecules, depending on the signal, we can also make a multiplex detections for the study, which the signal can be various, but it can target a multiple viruses. So in a single detection, we can detect multiple virus with multiple signal, but it's not cannot be achieved using signal with encapsulation nanoenzymes. That's I think what I'm thinking.
Very good, very good. I also have a question. Actually, I just put my question in the chatting list.
Okay. Is there any more time to answer? Okay. Actually, we also for the copper nanoflower, I also agree that the performance of the nanoenzyme is depending on the morphology of the copper nanoflower, but we didn't actually various the copper nanoflower size because actually it's quite fast reactions. But in the other times, we actually detect using copper ions. We compare with ions base and also copper nanoflower. But and it shows that the copper nanoflower, because it's the nanoenzymes, it have a higher activity compared only with copper ions, which means that only chemical reaction is good but not strong enough compared to nanoenzymes. Yes.
Thanks so much.
Yes. Thank you for the questions. Thank you very much for the questions. The reaction stop not because of it's quite different compared to enzymes, which not ELISA, which is we put S2SO4 to stop the reaction of the enzyme. But in this case, we use S2SO4 to stop the reaction also. That's why from blue it become yellow. It actually not stopping the nanoenzyme reactions, I believe, but actually it's stopping the quinone complex of the TMB. So the reaction itself will lead to the 450 rather than 655, and that would stop the reactions of the detections. Thank you for the questions.
Yeah, thank you for your answer. Let's move to the next speaker, master course student Jun Jie-hu from Shanghai University. Yeah.
应该就是屏幕。
这个不是正确。
哦，OK，屏幕不对吗？啊？哪个第二个？白板吗？不是屏幕，太快。
You can hear it. A bit noisy and delaying, but it's fine.
这个吗？对，我刚刚点的就是你点的是这个吗？对对，这个也点过。那我不知道哎。
刚才毛智慧怎么操作的？他不是做好了吗？
你们看一下。
不要用放映。OK。Please start.
我在哪？Okay. Hello everyone. My name is Junjae Hu. I'm a master student of Professor Chen. It's my honor to stand here to share my recent work with you. I'm going to talk something about specific intracellular binding peptide as PD-L1 antibody mimic, reduced binding capacity and intracellular region specific modulation applied to sensing research. Then I will discuss from three aspects: background, scheme, result, and discussion. First of all, cerebral PD-L1 is defined as PD-L1 on no cell membranes. It is memory divided into cleave PD-L1, secrete PD-L1, macro vesicle PD-L1, exomal PD-L1, and at present, cerebral PD-L1 has become a treatment official product of PD-L1 monoclonal antibody, and PD-L1 detection is an accompanying diagnosis of immunotherapy approved by the US FDA, which is good to guide precision treatment and optimizing efficacy. According to the 2020 Global PD-L1 Biomarker Detection Report, it is well known that its market demand is huge and there is a great research prospect. However, there are still detection limitations such as low concentration in some serum samples, high interference proteins, and high detection cost. Therefore, it is extremely urgent to develop a detection method with higher sensitivity, specificity, and detect clinical application value. And the PD-L1 immune binding molecules that have been developed can be divided into antibody, optimal peptide. But most of the three binding sites with PD-L1 are extracellular regions, and the binding sites are similar. One constitutes a sandwich method. There is the influence of Cedric Huygens and the artificial screen aptamers or peptide have weak binding force, which is likely to cause the situation that the target cannot be effectively captured. HIP-1R is a class of protein in the Huntington interacting protein 1 family. The latest study found that HIP-1R can specifically bind to the intracellular region of PD-L1 and guide the degradation of PD-L1 lysosome, thereby regulating the immunology killing function of T cell. Obtain the specific binding sequence of the PD-L1 intracellular regions of HIP-1R through lateral search, and design the specific intracellular binding peptide, which can be used as the second step specific molecule of the sandwich for PD-L1 detection. Its main advantage is its stronger binding force to the intracellular region of PD-L1, easy modification and labeling, and flexible normalization on nanomaterials. Gold nanoparticles are the nanomaterials that we chose to use SIBP for functionalization. Because our group has successfully verified that they can significantly enhance the SPR signal in the development of SPR sensor, so they can be used as an excellent signal amplification molecules for SPR sensor. Here is a brief introduction to my experimental scheme. Figure A shows the intracellular simulation of SIBP relative to HIP-1R, showing its binding specificity to the intracellular region of PD-L1. Based on the above background knowledge, sensor development is carried out. First, the sulfonic acid group of PSC4 is combined with the gold atom to fix it on the surface of the SPR gold chip. Subsequently, the exposed N group of the PD-L1 antibody and the classical array cavity are combined through host booster recognition. ESA was added to cells planned to prevent no specific binding of possible interfering substances in the serum. Then the target protein is added because the target concentration is too low. Functionalizing golden nanoparticle. Golden nanoparticle are to amplify the signal of the target, improve the detection sensitivity, and reduce the detection limit. Okay. First, the size-assessed nanoparticle were characterized through TEM. It can be seen the gold nanoparticle have good dispersibility and uniformity, and the particle size distribution is 5 to 10 nanometer. The size-assessed product was indirectly characterized by UV verse, DLS, state potential, and FTIR. The experimental result proves the successful modification of gold nanoparticle SIBP. Afterward, DLS was used to conduct stability studies. It demonstrated that the size-assessed material has good stability. SIBP is an immune molecule on the surface of gold nanoparticles, and its weak binding force will result in the inability to bind to PD-L1, and the detection sensitivity cannot be improved. Experimental results shows its KD is similar to that of antibodies. The binding force equivalent to the antibody shows that it has significant advantages in developing immunosensors and may effectively reduce the detection limit. And the modification stage of every step was monitored in real time, utilize SPR to verify the response process of the construct sensor. Therefore, the above results show that this method has good SPR feasibility. The gradual modification process of the decided sensor on the gold electrode surface was also corrected by CV and EIS. In addition, AFM also indicated the successful construction of the sensor and the experimental conditions of the sensor were optimized to achieve its max detection sensitivity. In order to effectively improve sensitivity, the decided sensor was utilized to the different concentrations of SPDL1 detection on the optimal condition. The limit of detection is 1.749 nanogram per milliliter. A previous study reported that the mean serum PD-L1 concentration of colon cancer patients approximately was 5 nanogram per milliliter, which was notable increased compared to those healthy donors. Figure A result shows that the sensor has great selectivity. As a consequence of the significant improvement of sensitivity of gold nanoparticle SIBP immunoassay, we found that the SPR angle shift caused by serum PD-L1 concentration of healthy donor and cancer patients was significant difference. This result establishes the feasibility of the decided sensor for future clinical text. This is the end of my report. Thank you very much for being here.
Okay, any question?
Can I ask one question? Oh.
Yes, please.
You sensed biomolecule or biomaterial by using SPR and electrochemistry at the same time, right?
아, 둘이 같은 데 있어서 더블링 일어난다.
姐回答，他问你用了电化学和SPR 的检测方法，是吗？
Yes.
Can we say that each other can affect to each other? That means SPR can affect to CB or CB electrochemistry can affect to SPR or something.
他是Sorry, I translate to him.
Thank you.
他说的是，他可能是理解错了，你并没有用电化学来去做检测，电化学仅仅是表征。他在问你电化学和 SPR 之间有什么关系，或者他俩有作为检测方法又怎么样？他理解的，你需要去解释，你并没有用电化学来去做检测，而只是表征。OK。
We only use electrochemistry method. So we not instead of a detection method.
없어?
Thank you. We didn't use the CV chemical assay to measure the PD-L1. We just use SPR. The CV and the EIS we just used to characterize the modification step by step, like that.
Okay, thank you.
Okay, thank you.
Can I ask one question?
Yes, please. Yes, please.
Okay. This PD-L1 is using for antibody mimic, right? And
yes.
Did you check the sensitivity of this system and using antibody?
Good question. 就是你用了 PD-L1，就是代替抗体。他问你是不是有和抗体比较了
？Yes, we have do experiment to compare the binding force of antibody with PD-L1. We found its binding force is similar to that of antibodies. they are on
用你的激光笔。
Okay, did you remember the KD value of affinity binding? KD value. KD value of
I
SPR.
can 我在哪里可以打
Okay, it's okay. It's not essential one. Okay, it's okay. Thank you.
Okay, thank you.
It's okay. Thank you.
You're going to be fine, don't worry.
Later he will show. He will maybe put it on the chatting side the value. Is there any question? If no question, let's move to another speaker. Yumi Kim from CNU. Welcome.
Okay. Hello everyone, my name is Youngmi Kim. I'm in the second semester of master course and I'm researching at Professor Jebam Lee's laboratory, Lee Lab.
Show your face.
Okay, today I talk about my research. The title is Magnetoplasmonic Metal Surface Sensor in Terahertz region. This work is being done with Da Zhongpang in Lee Lab. So presentation will be conducted in the following order. First, I explain the concept of experiment and then mention the experiment process shortly. Then we can discuss the experiment result. So, what is terahertz? Terahertz wave generally defined in the frequency range 0.1 to 10 terahertz lie between microwave and infrared frequency in the electromagnetic spectrum. With unique spectral properties, terahertz radiation permits many cutting-edge applications. First, terahertz waves are non-ionizing and non-invasive, so it's safe for biomolecules, and terahertz can penetrate for non-conductors, so it's stable for the inspection task. And third, because of unique spectral fingerprint, terahertz apply to molecular exploration and identification and imaging. However, terahertz also have some little disadvantages. First, terahertz absorb water well, so vulnerable to humidity, and also has a lack of productive source and sensitive detector. So I use metal surface to solve these problems. These metal surfaces are examples used in other research. Metal surfaces are two-dimensional, where surface counterparts of metal materials. They consist of periodically arranged unicell like this, and another shape. We can we can control overall spectral response and wavelengths of the device by changing the size, density, shape, orientation of the unicell. These metasurfaces are all responsive in the terahertz band. They greatly enhance their interaction with terahertz band. Here are all the terahertz metamaterial used in other research. Among them, I introduced the research of the terahertz metasurface using the plasmonic nanoparticles like my topic. In number 1 paper, they utilize the nanoparticles. They utilize the square matter patch array for terahertz smooth surface plasmon extinction. So this yellow one is gold nanoparticles and blue is avidin, the type of protein. So it shows the higher sensitivity when avidin binds to gold nanoparticles. And the second paper also used gold nanoparticles. The frequency shift attained up to 10 GHz with using gold nanoparticles, whereas without gold nanoparticles, only 4 GHz shifting. In both studies, nanoparticles are randomly doped on the metal surface. But in my research, nanoparticles are aligned to unicell in the metal surface. Then we expect to show better performance than randomly arranged. This is the nickel metal surface I used. On the polyimide substrate, nickel is parent, a thickness of 150 nanometers. In the naked, in the naked eye, we can't see anything on the surface chip, but when we magnify it, we can check the shape and size of the unicell on the polyimide chip. So this is optical microscope image, and these are the SEM image. SEM is scanning electron microscopy. We can also check the shape and size of unicell on metal surface. So this is an experiment step. First, I magnetized the nickel pattern chip using magnet for a while. The magnetization of nickel pattern can be seen by magnetic force microscope as following this image. So we can check before magnetization and after magnetization of nickel pattern. We can see something change. And then drop down magnetic nanoparticles on the nickel until dry. Finally, I can check the nanoparticles assembly by optical microscope and SEM. On the left is the simulation result of setting the magnetization direction to the x-axis in the nickel pattern. So this is x-axis direction. And these images are SEM image. Nickel is magnetized through the external magnetic field in this direction, x-axis, and coated with magnetic nanoparticles. So I use silver ionoside nanoparticles. By comparison with bare chip, we can see that nanoparticles are coated only the magnetized nickel pattern. With the same SEM image as the previous slide, just magnified. So depending on the direction of the magnetic field, the end of horseshoe was connected to the assembly of nanoparticles. This time, I set a different direction for the external magnetic field that magnetized the nickel. One is set to the x-axis and the other set to the y-axis. So when I set the x-axis, the external magnet is here. One is here and the other is here. And as a result, we can see that the shape of the nanoparticles has changed. Under each conditions, the magnitude of the resonance peak shifting in the terahertz different. Figure A and B are same nanoparticles but different concentration. At low concentration, the frequency shift only 26 GHz. By comparing the B and C, we can see the difference. The direction of magnetization affects the terahertz resonance peak. In graph C, with the magnetization direction set to the y-axis, the frequency shift attained up to until 124. Finally, figure D is the result of non-plasmonic nanoparticles to check the plasmonic effect. So you can see that the peak shift has decreased compared with the graph B. Based on this research, I'm going to try biosensing. So through the complementary coupling RNA and picot sequence, the CTC RNA is detected. First, I fix the molecular beacon on the metal surface and then combine the RNA probe to detect them. Finally, the degree of peak shifting show greater result than previous other research. So in conclusion, I found out myonetoplasmoid nanoparticles are improved the performance of nickel pattern, and compared to other magnetic nanoparticles, the performance was the highest when coated with the plasmoid nanoparticles. And this myonetoplasmoid metal surface has been proved to available as a sensor through the binding of nanoparticle and target molecule. So I need more experiment for the sensitivity and selectivity test for the biosensor. Now my presenter ends here. Thank you for listening.
Okay, thank you. Very nice picture. The
Come to Korea, please.
Oh, we want, but any question?
Yes, hello.
Yeah, please.
Can I ask a question, please?
Yes, please.
Okay. Thank you very much for that good, wonderful presentation. I want to ask just two questions. The first is I'm very interested in your simulation that you showed in one or two of those slides. So yeah, very well. So I want to ask, what simulation software did you use? Is it FDTD or the finite element method?
The simulation conducted by ComSol.
Okay.
Yeah.
ComSol multi-physics.
Okay, ComSol.
Yeah.
Okay.
Yeah.
All right. Then have you also considered integrating graphene with your material, since they also exhibit some tetrahedral kind of plasmonics in the tetrahedral range? Have you ever tried or thought of incorporating graphene materials, the nano ribbons or the different nanosheets of graphene?
magnetic simulation. This simulation result only set the direction of magnetic field. I'm not trying yet using nanoparticle assembly on the metal surface by simulation.
Okay. So do you have the capability to do this simulation in your present laboratory? You have the software capabilities or the provision?
Yeah.
Okay. So I think I might like to discuss with you probably after this presentation.
Okay.
On maybe.
Okay.
I will discuss with Professor Park to also discuss with your Professor Lee. Thank you.
Thank you.
Can I ask a question?
Yes, please.
How did you combine magnetic beads and RNA?
On the surface of nanoparticles, I try to fix the hydroxy group on the nanoparticles, And then using EDC and NHS compound, I conjugate with RNA and magnetic nanoparticles.
Okay, thank you. Thank you so much.
Thank you.
Okay, I have one question.
Yeah.
As we know, the water will affect the THC detection. So, how can you to detect the biomaterial in your system? The water, how to?
Because terahertz source is very weak, low, so I use metal surface to enhance the peak resonance. But biomolecule, because terahertz have some spectral fingerprint to detecting biomolecule. I use nanoparticle to detect biomolecule.
Yeah, thank you. I mean, the water. It seems to similar to SPR, but in SPR system, the water doesn't affect the detection result. But in THC, I know, as I know, the water will give the big background for the detection. So I don't know in your system what have you done to limit how to remove the water effect.
In my terahertz is very absorbs where water. So when I magnetize the nickel pattern, I dropped the nanoparticle solution and I dry until the water is dry. So finally, the nanoparticle assembly on the metal surface, not including water.
So every step you should make sure the water evaporated thoroughly for every step, right? Okay, thank you.
Thank you.
Is there any question? Good talk. Yeah. Okay. No questions. Thank you for Yumi Kim's presentation. So now is the intermission. We have a 50 minutes break. Yeah. Let's take rest.
저거 됐어?
Yeah. After 30 minutes, we'll have lunch time.
Okay, one more time. Everybody ready?
Everybody's ready.
Ready? Ready?
Yes.
Okay, Isaac also. Okay, let's move the third session. This session for master and undergraduate student. However, we have very tight schedule. 3-minute talk and 2-minute Q&A. Therefore, if you don't give time, your lunch time will be shorter, right? Okay.
Really not.
Okay. First talk is from Shizuoka University, Keita Isago, Mr. Isago. Title is Ultra-Sensitive Electrochemical Virus Detection using platinum nanoparticle, nanocatalyst, and catalytic reduction of nitrophenol. Are you ready? Go ahead. Go ahead. Isago, go ahead.
Just move on. Good morning, everyone. I'm Kida Isago, a bachelor student from Shizuoka University. I'm really happy to join this e-workshop. So I will talk about ultra-sensitive electrochemical virus detection using PTFE34 nanocatalyst and catalytic reduction of nitrophenol. Nowadays, COVID-19 is spreading all over the world, but development of vaccine and medicine against COVID-19 will take enormous amount of time. So we can say that early physical isolation is currently the most effective measure to prevent the spread of disease. However, RT-PCR requires large-scale equipment and highly skilled professionals. For this reason, there is a need to develop new detection technology to replace this one. Firstly, we fabricate this type of PTFE34 because this type catalytic ability is higher than other shape. Next, we attach antibody to PTFE34. After that, PTFE34 complex and antigen from monkey were mixed and combined. It was separated from others by magnet. Finally, the complex was combined to secondary antibody on the electrode. This is TEM image. We can see the structure. Left picture is only MMP, it's magnetic nanoparticle of Fe3O4, and right picture is complex of MNP and tiny platinum solution in red squared. This is detection part. The peak of aminophenol is increasing with increasing of concentration of virus, because when there is more virus, platinum as a catalyst is also more on the electrode, and it helps to convert from nitrophenol to aminophenol. Then calibration curve is also showing same. This is selectivity. Selectivity was checked with 7 VLP, including HEVLP. When HEVLP was set to 100%, other viral current was under 20%. This is inclusion. Through this experiment, I can say that we fabricated a nano biosensor for HEV detection and PTMMP successfully. PTFE34 are used for catalytic reduction for nitrophenol. The developed sensor can detect HEVLP from 10 femtogram to 10 nanogram, and PTFE34 based sensor exhibit good selectivity. Thank you.
Thank you very much. Okay, a very short time, therefore, please, some question.
I have a question.
Okay.
How does the antibody immobilize on the PG at magnetic nanoparticles?
First, I made ATMMP. It's amino-based terminate magnet nanoparticle. After this, we add platinum, just platinum ion. So we complete to make its complex, magnetic complex. It makes sense? No?
That's good. I also have a question. So PT is coated on the surface. And yes. What about the magnetic nanoparticle itself? It has a kind of ability to oxidize. Have you checked?
Sorry.
So just see my chatting.
Okay.
Is it possible to be oxidized by the MMP only? MMP itself is a good oxidizer reducing agent. I'm just wondering.
Which one? So where is your question?
MMP is oxidized or not? Is
it possible to be oxidized?
Yeah, from Jebamni.
No. I don't think so for nitrophenol. So. Yeah. We need platinum or other gold.
The data. Okay, thanks so much.
Okay.
Thank you.
Okay, no more time. Thank you, Isago.
Very good talk.
Okay.
Thank you so much.
We are moving to next speaker. Next is from Shanghai University. Mr. Miss. I don't know. Miss Yu. Title is Function-wise magnetic with oriented ligand to detect LEC2 by SPL assay. Okay, ready? Go ahead. Please go ahead.
Sorry, wait a minute. Oh, God, this one. Okay. Oh, it's okay.
Okay, go ahead.
Sorry, there's some question. 怎么会这样呢？我也不知道。如果可以继续就继续吧。你们那儿对的吗？ Okay. Good afternoon, everyone. My name is Han Zhu, and I'm come from Shanghai University. I'm very honored to share my work at this meeting. My topic is functionalized magnetic nanoparticles with oriented legend to detect LEC2 by SPR assay. Sorry, there's some problem on my computer. Okay. Liver fibrosis is a disease of excessive deposition of extracellular matrix such as collagen and fibronectin in liver tissue as a result of repeated liver injury in patients with chronic liver disease. The most common causes include chronic viral hepatitis, alcoholic liver disease, non-alcoholic steatohepatitis, and autoimmune hepatitis. If the damage factors persist and can't be removed, the process of fibrosis will develop into liver cirrhosis gradually. Liver fibrosis itself has no obvious clinical symptoms, and there is no specific clinical diagnosis so far. The specific of 4 tests of liver fibrosis is not high and mostly only for clinical reference because of the greater impact of liver inflammation. Recent studies suggest that LEC2 is a functional legend of Taiwan, a poorly characterized endothelial cell-specific orphan receptor. Upregulation of LEC2 is associated with advanced human liver fibrosis staging. Targeting LEC2 Taiwan signal may represent a potential therapeutic target of liver fibrosis, and serum LEC2 level may be a potential biomarker of the screening and diagnosis of liver fibrosis. 我看不到激光笔怎么办？ In this work, a sensitive SPR sensor based on aptamer-oriented Taiwan on magnetic was developed to achieve quantitative detection of LEC2 as shown in this page. And PSC4 was anchored on the gold chip at first, and then LEC2 could bind with PSC4 through hydrophobic interaction and host get recognition to modify on the gold chip. I can't. 我能找到激光笔吗？不行 ，OK。Human IgG1 Fc fragment specific aptamer was connected to the magnetic nanoparticles with server cores through an activation using the EDC NHS to activate the carboxyl group of magnetic nanoparticles. Then the specific interaction between aptamer and Fc tag on Taiwan protein achieved the oriented immobilization of Taiwan protein on magnetic nanoparticles, which enhanced the bending ability of protein functionalized magnetic nanoparticle with target. The magnetic separation can be performed to separate and enrich the target from the complex serum environment of human. The constructed sensor have good visibility and can be applied to the clinical detection of LEC2. And this is some of my experimental results. Thank you for listening.
Okay, thank you very much. Okay, have some question? Somebody question?
A question.
Okay.
What is your advantage compared with another technology?
Pardon?
Okay. What is your advantage compared with another technology?
What's the 我大概知道，maybe the oriented immobilization of the protein on nanoparticles could enhance we think it could enhance binding efficiency between the receptor and ligand, or antibody and antigen. 我们的电脑怎么回事？
你的结果都给大家展示一下，你没有讲。
我们的电脑出问题了，我这里屏幕是卡住的。
The computer.
Okay, now some trouble.
Yeah, maybe.
Okay. Okay, so okay. Thank you very much. I think we have to go to next. Okay. Next talk is from CNU, Mr. Picha. Right? The title is argon plasma exfoliated NiFeCOOH nanosheet for OER in alkaline condition.
Yeah.
Are you ready? Go ahead.
Okay, thank you very much. Hello, everyone. My name is Brian Baisa. I'm a PhD student in chemistry department under supervision of Professor Lee. Actually, my title is not exactly for the biosensor, but it's not far from, because the catalyst is not much far from the area. So our lab is a multidisciplinary lab. We are doing on different areas of research. Among that, energy is one part. So we welcome any firm who wants to collaboratively work with us on the areas of energy and other areas of research. So today I'm going to present one of our work, argon plasma state exfoliation of nickel iron cobalt LDH for enhanced oxygen evolution reaction in alkaline condition. As you know, energy is one of the current global issue because of the issues related to the global climate change. There is an urgent need to transform the current global energy into green and renewable energy. So among the sustainable energy sources are we have huge amount of renewable energy sources. So among them is hydrogen energy. So hydrogen energy can be produced from different sources. Among them is water splitting. So in this process, in order to split water into hydrogen and oxygen, the process is an uphill process because it requires huge amount of energy. So in order to reduce this energy, we need a catalyst. So previous catalysts are mostly the very expensive catalysts, but currently there are researches ongoing to produce catalyst from the transition metal oxides. So these transition metal oxides are good, but still they are not up to the required level. So we need optimization techniques among them. Different techniques have been applied. Among them is the exfoliation process. In this process, the exfoliation, there are different techniques of exfoliation. So the process leads to the formation of the ultra-thin nanosheets. So with this, we exfoliated nickel, iron, cobalt, LDH with argon plasma. So we finally got an ultra-thin nanosheets, which is very thin, around 1 nanometer. So this technique is very important in catalysis because thinner materials are very good for oxygen evolution reaction because they can easily expose to the electrolyte. So as a result, the reaction will be highly facilitated. So with this, when we compare the treated with the untreated one, as you can observe, the treated one has improved electrochemical activity compared to the other one. So we also check the thermal flows and as well as the impedance. So as you can observe, overall the activity and of the material is improved due to the exposed surface activity of the material. Finally, we have checked also, because stability is one of the basic issue in the electrocatalysis for water splitting. So we have checked our material for stability. So the material has a good stability. It's served for almost 100 hours without almost losing this activity. So this is the activity before and after the electrochemical test. So with this, I will conclude my presentation. So we have produced an ultra thin nanosheet, which is very thin, around 1 nanometer, and the material has, due to this plasma treatment, the material has showed a high activity compared to the untreated one, and has also showed a good stability. So thank you very much for your attention.
Thank you. Thank you for your good presentation. Okay, open the presentation open for discussion. Have some question? Somebody?
Tsuruga desu.
Oh, okay. Go ahead.
Thank you for wonderful presentation. I don't have any knowledge about this field, so I have a simple question. Is there any detection system using this your nanosheet?
Detection system?
Yes, virus detection system.
I'm not sure actually, but we can use maybe for biosensing. I didn't think just applying for that purpose, but maybe in future we will consider that part also.
Okay, thank you very much.
Okay, he's only thinking about virus sensing. Okay. We have no time, no more. Thank you very much. Okay, we go to next presentation. Okay, from Shizuoka University, Mr. Tsuruga. Title is high sensitive on-site detection of norovirus. Already go ahead. Please share file. Please slideshow. Okay. Yes, you are mute now.
Sorry. Hello everyone. My name is Kenta Tsuruga. I'm a bachelor student in Shizuoka University. This time I talk about on-site virus detection. First, a brief introduction to the norovirus that is target in my work is told. Norovirus is known as the main virus of infectious gastroenteritis, which is highly infectious in the society from the contaminated surface and person. Currently, there are two methods in detecting noroviruses, RT-PCR and EIA kit. However, each of these methods has problems such as sensitivity or time consuming. So higher sensitivity and rapid biosensor is required. In the developed biosensor, gold polyaniline is used for its good conductivity and as an anchor site for NSGQD. NSGQD is used for conjugating antibodies. Besides that, the N and S atoms, which are doped on GQDs, changes the electronic properties and greatly improves the electrochemical properties. In addition, the doping of sulfur atoms provides affinity to gold in the polyaniline. To fabricate the electrode, polyaniline was deposited on a commercially disposable electrode by electropolymerization, and then antibody NSGQD gold polyaniline was deposited above the polyaniline. When the electrode is incubated with the target virus collected from wiping, the target virus binds to the electrode surface, and the virus is detected by observing the change in impedance value. This is the results. First, the one on the left is a graph showing the change in impedance value when a diluted NOR-VLP solution, 10 femtogram per milliliter to 1 nanogram per milliliter, is used for direct incubation. For the calibration curve, the x-axis shows the VLP concentration, and the y-axis shows the percentage increase in impedance value compared with control one. As can be seen from the calibration curve, a concentration-dependent increase in the impedance value was confirmed. In the wiping study on the right side, a cotton swab was used to wipe off a part of the prepared compartment. So it was expected that the signal would be smaller than that of the undiluted solution. The results obtained were as expected. The maximum increase in the impedance value of the undiluted one was 21.8 times, while that of the wiping survey was 9.7 times. These results suggest that this detection system can be observed an increase in impedance values according to the amount of virus. Conclusion, we have successfully fabricated antibody NSGQD gold polyaniline electrode for norovirus detection. When virus attaches to electrodes, the charge transfer resistance increases with respect to virus concentration. Norovirus can be detected in the linear range of 10 femtogram to 1 nanogram. We have also detected norovirus using wiping test and found almost similar results. So in future, we will apply the developed sensor for on-site norovirus detection. Thank you for listening.
Thank you very much. Okay, we have some time to question time. Somebody question?
Some questions I added in the chatting.
Chatting, okay.
So why you do the combination of many nanomaterials and polymers? The reason is improve the conductivity.
Yes, I use the nanomaterial complex for improve the conductivity of the surface of electrode.
Okay.
Yes.
Yeah.
But Suruga, you can. Why? Why GQD? Why gold nanoparticle?
Right. Yeah, that's the question too. Yeah.
What is the?
It means NSGQD.
Yes.
NSGQD. In my study, we need the gold polyaniline NSGQD complex. So NSGQD's meaning is for anchor site. S atom is the anchor site for the gold nanoparticle in polyaniline, and N atoms means the improvement of the electricity of the
GQD.
Yes.
Yeah, that's okay. And antibody is also conjugated on your NS of GQD, right?
Yeah, GQD is COOH.
Okay.
Using ND-ED.
Okay, thank you.
That's good talk.
Okay, Okay, it's okay. Okay. I think
Thank you very much.
no
No
more. Okay, question. It's okay. Oh, Mr. Tsuruga, thank you very much.
Thank you very much.
Okay, move to next presentation from Shanghai University, Chang Chen. Miss Chen, right?
Yeah, yes.
Mr.
Yeah, Mr.
Okay, title is Magnetic Nanoparticles Assisted Sensitive Detection of Nitrate Alpha SYN in Blood based on a sensitizing electrochemical laser. Okay, please prepare and go in. Mr. Chen. Okay, go ahead. Please share your file.
Okay. Champion. 怎么弄呢？在哪champion？
Sing Chen. You can start. Don't worry, be happy.
Good afternoon. I'm Chang Chen, a master student of Shanghai University. It's my honor to be here for sharing my recent brief work progress. According to the literature, alpha-synuclein is a soluble protein expressed in the central nervous system. It performs a variety of biological functions in the brain, such as the maintenance of the synaptic structure, the regulation of dopamine uptake, and other positive effects. But when alpha S1 aggregated abnormally or misfolded, it can cause the many disease like Alzheimer's disease, Parkinson's disease, and other neurological disease. Negative alpha S1 was an undesirable modification associated with oxidative and negative damage and highly transferable protein. It can be found in bloody fluids like blood, saliva. So we designed an electrochemical method to detect this protein to predict the occurrence of disease. Here is my scheme, and showing the scheme, we use the golden nanocomposite as a center platform for immobilized anti-nature alpha S1 to develop a natural alpha S1 immune sensor, which greatly enhances the immunoassay performance. Gold nanoparticles have a faster electron transfer rate and a larger specific surface area. The incorporation of supermolecular offers abundant the cooperation of supermoleculars offers abundant binding sites for immobilized antibody by introducing sulfonic acid groups, which keep the activity of antinatural alpha SOI by no covalent interaction force. Anti-alpha SOI modified magnetic nanoparticles have been used as single amplification tags, and its unique spherical structure and high conductivity show excellent stability, and the net decrease in charge transfer resistance. I think this will improve the clinical application value of precision medicine. These are some of my experimental results. Here, characterization of the nanomaterials, and this is fabricability of biosensors. Thank you for your listening.
Thank you. Very good presentation. Okay. Now, somebody ask a question?
What is the height to affect the SPR signal from the gold film? So in your experiment, you stacked gold and antigen antibody, then magnetic nanoparticle. Then want to see the some resistance changes, I believe. So I'm just wondering how many layers can be stacked.
陈强，把你的那个 PPT 拿出来。不是这个 result， 再往后，李教授问你用几层，就是你用多少层的金胶？
金胶。One layer.
Only one layer?
One layer.
Extremely sensitive, you mean?
Okay.
I see. Thank you.
I introduce them. We first outside to make the network of the gold. Then we just drop on the electrode. It's not one layer. It's just like a small mountain of gold nano.
I believe so.
Yeah, on the surface. But actually, we just find the conductive was improved very much. Here you can see the EIS data. After adding the gold nanoparticle complex, the EIS data is the conductivity is better than the bare gold.
Yeah, I see. We are hungry.
Okay. Okay, nobody? Nobody? Okay, if possible, one more thing I can ask. One more thing. Okay, already. Okay. This molecule is very high, big one. Small molecule, the size.
问这个蛋白的大小，陈强。
老师。
他问蛋白的大小大概多少千刀？
大概多少千刀？蛋白。for 16 dollars.
16.
16 kilodalton.
40.
Oh,
pretty big. $14.
Okay. And you can detect this from blood sample?
Maybe.
你能够在血清里边检测它吗
？Yes.
Then I think many other interference effects you can.
Yeah, I think so.
Problem, right?
它的影响物质你怎么去避免的？ 你用什么做 blocking 的？有 blocking 就是你
BSA.
BS, okay, BS, okay. It's okay. Okay, thank you very much. Okay. Okay, next, Mr. Lee already stand by now. Okay, next talk is from CNU, Mr. Lee, Dongyu Lee. Title is Plasmonic Nanostructures for Biosensing. Okay.
Good morning to Vietnam and China, and good afternoon to Japan and Korea. My name is Dongyu Lee, and today I will introduce my works briefly. Title is Plasmonic Nanostructures for Biosensing. Normally, SPR sensor is made up with gold nanofilm. Gold nanofilm can absorb specific wavelength light, so if that wavelength red shift or blue shift, we can detect that peak shift to detect biomolecules. When biomolecules comes to the surface of gold film, peak shift happens, and to make more sensitive sensor by using this material, researchers have tried to confine electric field, and designing this confined electric field is necessary part of making more sensitive and more selective biosensor by using plasmonic materials. So researchers have used this kind of achiral structured nanoparticles to detect achiral biomarker, and by using same material, they can detect chiral biomarker by using circular dichroism signal. And also they wanted to detect more sensitively chiral biomarker. They tried to design and synthesize chiral plasmonic structures of gold or silver nanoparticles. And what I did is making this chiral type structure and analyzing their optical properties by using simulation method, which is finite element method. In finite element method, we draw simplified structure of our system and give them physical properties, and divide these structures into smaller structures, and we calculate solve partial differential equation by using our computer, and result always looks like this. We made silver core Fe04 shell Gaussian nanoparticles. This has magnetic properties and plasmonic properties at one body, and the color of this material is tunable by changing the structure of Fe04 shell, and we can assemble by using external magnetic field in 1D or 2D or 3D chiral structures. Today I will introduce the chiral structure of this nanoparticle. Silver core Fe04 shell nanoparticles can be aligned in following the direction of the magnetic field flux between magnetic bar. When magnetic bars are parallel, magnetic nanoparticles also assemble into linear structure, but when we give them twist, when we give an angle between magnetic bar, nanoparticles assembly also twist, and we can see the chirality by using circular dichroism signal, and depending on the angle, the circular dichroism signal, which means the chirality of the structure can be tuned by changing the theta. We simulated that system by using FEM method I previously introduced. We characterized the building block of this system, which is silver core Fe04 shell nanoparticle. Because this structure color can be tuned depending on the shell's porosity or structure, we brought the concept of effective refractive index to define their porosity as an optical simulation point of view. So we found that our material has this kind of relation between effective refractive index and peak position. We made, by using this material, we made these three types of arrangement examples, and we simulated by FEM method, and we get circular dichroism signal by averaging these kind of three representative kinds of arrangements. And we can also see the electric field distribution, which means on white side, the electric field is strong. So if the biomarker is on this side of electric field is higher, we can detect more sensitively. In conclusion, to enhance sensitivity of biomarker, we combine electric field and it should be designed, and we analyze electric field distribution and absorption spectra by using finite element method. And using this method, we can predict an optical properties. Moreover, we can design appropriate structures for specific biomarkers. Thank you.
Okay, thank you very much. Very huge amount of work, very short time. And we have almost too delayed, therefore only one question if you have.
Ask question.
Oh, okay.
Dongyu, I have
Yes.
a question for you. It's possible to make a very good aligned film for your nanoparticle?
Very good aligned. Can I get?
Yeah, one by one, just one layer.
Yes.
It's possible.
Yeah, it is possible. We can align by using magnetic field and binding with the substrate, and then we can stack second layer and third layer. That is also possible, but the better this system is better because it is tunable in real time. Thank you.
Okay. One more question.
Yes.
You mentioned you can make the 2-layer or 3-layer. So what's the difference for the multi-layer or 1 layer? Is there any difference for the detection? For example, sensitivity or any other?
In my opinion, we can consider the light intensity and electric field concentration. In electric field concentrations point of view, the stacking more good. Stacking more is better, but light cannot penetrate easily when it is too thick. We need to consider about that, and we can get appropriate condition.
Okay, thank you.
Thank you.
Okay. If you have some question, please using chat. I think Mr. Dr. Lee can answer. Okay, therefore we delayed almost 15 minutes as scheduled. May I passing this microphone to Professor Lee?
Too much over.
Professor Lee?
Okay.
Okay.
Just do you want to keep the time for 80 minutes, or you want to do start 2:20 exactly?
Okay, 2:20. Okay, as scheduled 2:20. Okay,
lunch
we'll start.
time.
Okay.
Yeah, let's start
Okay,
at
thank you.
2:20. Yeah.
Okay. Enjoy
Thank you
lunch.
much. See you later. So far, so good.
Hello everyone, I'll present on this tema. I use Cain-Parovirus CPV as a VLP capsid. It belongs to the genus of Parovirus.
Writing's not.
Hello everyone, I'll present on this tema. I use Cain-Parovirus CPV as a VLP capsid. It belongs to the genus of Parovirus and is a highly contagious infection. Hello everyone. I'll present on this tema. I use Cain-Parovirus
Good afternoon, everyone. I would like to start my presentation. Today, I am here to talk to you about expression and purification of white spot syndrome virus antigen protein using silkworm expression system. WSSV was firstly reported in Taiwan in early 1990s and later had spread to other aquaculture regions, causing a huge damage in shrimp industries annually. Many studies revealed that this virus contains at least 5 major billion proteins, including VP15, VP19, 24, 26, 28. Several studies have reported that these proteins can increase resistance to the WSSV. In this study, WSSV antigen proteins were expressed
오조도모 존 아카두. 아카두. We are waiting for Professor Chen to organize the first session. Or I may change the time. Okay, Chen is coming.
Yeah. Okay. Yeah, good afternoon, everyone. Let's start the next session. Okay. Next presenter is from the Shizuoka University. Ojoduma John Okado, please.
Okay, good afternoon, everyone. I hope you can see my slides. Please, already share.
Good.
We can see it. Yep.
Okay. Good afternoon, everyone. I am Ojodomo Achadu, and I will be presenting my talk today, which is on the recent developments in surface-enhanced Raman scattering-based virus detection, smart tags, nanotags, hotspots engineering, and opportunities for future technologies. So, firstly, please give me the opportunity to introduce myself to you. So, I'm currently a JSPS postdoctoral research fellow in the Green Chemistry Division at the Research Institute of Green Science and Technology, Shizuoka University, under the supervision of Professor Enoch Waipak. So my JSPS work is largely based on nanogels loaded with plasmonic molybdenum trioxide quantum dots for virus detection. So I also want to briefly explain to you my research journey to science, which has been quite an interesting one that has saw me move across 3 continents. So my first postdoc was in South Africa, where I backed my PhD degree in 2007 in chemistry, and also University of Bordeaux in France, where I spent 9 months, and was cut short due to my award of the just JSPS currently on now here at Shizuoka University. So I will be majorly talking on the Raman spectroscopy. I will not draw much on the biosensors design because it has been really touched by other earlier presenters. So for my PhD work, this is the major areas that I focused in: luminescent optical biosensors. And we also did a lot of work on PDT, which is the photodynamic therapy for drug delivery, photonics material, which is the nonlinear optical materials fabrication using complex organic microcycles such as porphyrins and body peas. We also did a lot of studies on electrocatalysis, and also a little bit of photophysics studies of these complex molecules, graphene quantum dots, CDSC quantum dots, and the rest with these complex materials. So based on this knowledge and the experience that I've gathered in optical biosensors design or optical studies and photophysics of nanoparticle materials, I find quite interesting the principle and the principle of or the technique, the optical technique, which is the surface enhanced Raman spectroscopy. So this is just to give a little bit of background to some of the students and some of us that are not very familiar with the concept of surface enhanced Raman scattering. So what happens typically is that when a molecule is excited, they usually there's some kind of electronic excitation. But then in normal Raman, what you have is that you have some kind of what we call the inelastic scattering. The wavelength or the energy of the excitation source is not the same as the light that is being scattered. So this kind of scattering is referred to as inelastic scattering, whereby you can have either shorter wavelength light being emitted or longer, depending on the process that is taking place, and you can have or it's largely due to energy losses. So, but then this actually complicates the use of normal Raman spectroscopy. But then in the presence of, it was discovered that in the presence of some plasmonic nanomaterials, such as gold, silver, and the emerging semiconductor nanoparticles, you can have what we call the plasmonic coupling effect due to the electromagnetic, they actually have some unprecedented electromagnetic coupling with molecules. So just like you see here, when you have these same molecules that exhibit very low Raman signal or very weak Raman light scattering, but in the presence of plasmonic materials, they can actually have significantly higher scattering or better scattering, which means they have enhanced Raman scattering in the presence of these plasmonic materials. So, and the principle or what is happening is due to the fact that we have some plasmonic resonance effect of the metallic nanoparticles. So they can lead to what we refer to as the electromagnetic enhancement. Or in some cases, we can also have what we call the charge transfer directly from the surface of the nanoparticles or semiconductor material or electron-rich species interacting with the molecules to result into what we refer to as the chemical enhancement. So these are basically the two mechanisms that are at play when you have a surface enhancement, the surface Raman scattering of molecules. But then most people are quite only familiar with the plasmonic resonance or the coupling and all that. But then semiconductor nanomaterials too can also exhibit this, some kind of scattering effects that can lead to surface enhanced Raman scattering. So this kind of we see that we can have some different kind of plasmon driven performances due to the presence of metallic nanoparticles or semiconductor nanoparticles. So one of the concepts or one of the processes that is typically exhibited is when we see some far field scattering, which is you can have some kind of distance dependent sort of coupling, plasmonic coupling. Then we can also see some near field whereby the molecules are typically absorbed on the materials. And in this case, due to the closeness, they can also exhibit some kind of plasmonic effect or maybe some enhanced Raman scattering. They're typically exhibited by semiconductor nanomaterials or some electron-rich species is the hot electron transfer, whereby due to closeness, there can be effective electron transfer or charge transfer, as the case may be. Then the usual or the quite familiar one, which is the plasmonic resonance energy transfer, where you have some plasmonic and electronic coupling, leading to either good enhancement in surface Raman scattering or Raman signal of close by molecules. So this concept is far used in it has found so many applications in biosensors, in the field of drug analysis, in general analytical chemistry endeavors or detection system. This is because most of this system can be designed in a label-free systems of detection, and they are quite very sensitive as well. They can actually be tailored down to single molecule detection, and even single virus detection has also been reported using surface enhanced Raman scattering. So I will go straight to talk about, for my work, I focused my GSPS research work on principally using some molybdenum plasmonic nanostructures, the quantum dots, nanocubes, and the rest. So the choice for molybdenum trioxide is, of course, the diversification or the branching into discovering newer materials that can exhibit some comparable plasmonic effects as gold or silver nanoparticle is also quite interesting. Some of this material, the gold nanoparticle is, as we know, is particularly quite expensive material, and also their toxicity is also kind of the level of toxicity that they pose to the human system is also quite questionable. But molybdenum nanomaterials are and they're also quite very cheap material. They're earth abundant. So molybdenum nanostructure typically exhibits single layer morphology and also some few crystalline structures. So I've indicated some of the crystalline structures of molybdenum based nanoparticles. So they can have some different crystal arrangements and structural arrangements that gives them some kind of very interesting properties. So why molybdenum trioxide is because the presence of oxygen can lead to what we refer to as the oxygen vacancy that leads to some kind of free carrier electron. It's been used for a lot of studies where you require some free electron transfer process or surface carrier absorption. And the fact that they're also semiconductor-based material also makes it quite interesting because they can be used in various fields, photocatalysis, in catalysis, and in a host of other optical or optoelectronic applications. Then also very interesting for molybdenum material is the fact that they exhibit some UV visible, some visible, and their plasmonic resonance typically occurs in the visible and near IR region. The NIR region is quite very interesting for biological studies. So it means this material can typically be used for a lot of bio applications. So this is just a brief summary of my interest in molybdenum trioxide, and this is also quite emerging in surface enhanced Raman scattering, which we are trying to modify with different materials and to exploit their full potential in biosensors design. So, well, they are typically prepared just the way you prepare other carbon-based quantum dots, majorly where you can have some different techniques or processes, such as the hydrothermal and the subthermal processes. We can also use some photoirradiation processes for their synthesis, and oxidative exfoliation of large sheets of molybdenum disulfide or molybdenum sulfide has also been reported. Then also chemical and chemical and physical etching of bulky materials can be cut down via the top-down approach to actually synthesize some molybdenum trioxide nanoparticles. So they have numerous source precursors materials that can be exploited, that can be used. Some salts, ammonium. The common one is the ammonium salt of molybdenum. They can be easily oxidized by hydrogen peroxide, and from there you can do some hydrothermal treatment or further oxidation and cutting process to achieve some plasmonic molybdenum trioxide quantum dots. So this is just to mention a few of the synthetic processes. So I've largely used the hydrothermal process, the photoirradiation process, and the oxidative exfoliation from my preparation. So I will now show you a result of one of the molybdenum QDs that I've synthesized quite recently, which I've used in the detection of biosensors by encapsulating them in some polymeric nanogels. So typically, the synthesis actually is confirmed by the presence of the surface and the elemental and atomic composition of the molybdenum is confirmed by the presence of the molybdenum 2p and 3d peaks, and also the deconvolution of this peak, XPS peak, also shows us the different oxidative states of the molybdenum nanoparticles, and this is actually due to the fact that we have them in their oxides. Then the TEM image also shows us a very good size distribution of the molybdenum nanomaterial, which is quite expected. And very interestingly is that we have a very good absorption peak which shows the plasmonic resonance between 600 to 700 nanometers. There's some weak plasmonic absorbance above 700 nanometer, but we focus on this. And the reason why this is very exciting for me personally in my work is the fact that I can do my surface enhanced Raman scattering with my 785 nanometer laser, and I can have very, very good high intensity of the Raman scattering. So then this brings me now to my major discussion, which I talk about the nanogel encapsulation of molybdenum trioxide for virus detection. So this concept is actually based on two principles. Fabrication of CES nanotags, which I'll discuss shortly. Then the concept here was to use a pH-responsive nanogel. And the pH-responsive nanogel is actually used as a protective shell to encapsulate the molybdenum trioxide from interaction in clinical sample matrix, or to shield them from, to protect their integrity, because they are usually being disturbed, or their interaction or their properties perturbed by matrix or high ionic strength or high ionic solution. So we also integrated some 2D nanostructures as substrate so that we can have what we also call some gap enhanced Raman spectroscopy. So I also want to talk briefly about Raman nanotags for the benefit of some of us that are not quite familiar with this system. In my earlier slide, I showed you that we can have some molecules, especially some aromatic compounds. They have very weak scattering in normal Raman spectroscopy or under Raman measurement. So for example, for you to form a Raman nanotag, you have to be able to conjugate what we refer to as a Raman probe, with a plasmonic nanomaterial. In this case, we conjugated molybdenum QD with 4-mercaptobenzoic acid. So 4-mercaptobenzoic acid gives some very weak Raman signal in the normal Raman measurements, which is the black line down there. But then upon conjugation with molybdenum trioxide, based on their plasmonic and the charge transfer effect, they can significantly jack up or enhance the signal of molybdenum to measurable and very distinct levels. So the combination of your Raman probe, by Raman probes are molecules that can have specific and distinct absorption or that can exhibit some Raman spectra, or based on the electron and charge transfer within their nanostructures, within their molecular structures. So when these molecules are conjugated to plasmonic materials, you have your CES nanotags. So next is just a brief overview of the kind of system that we try to design. We have a nanogel that is surface functionalized with antibody for biotargeting of analyte of interest, in this case, which is the virus. Then one of the grand strategy in my work here is the use of magnetic nanoparticles that is also functionalized on the surface with a complementary biotargeting antibody, and also some maleimide functionalized groups. So this maleimide functionalized group have very strong affinity to interact with thiol compounds at a certain pH. So what we did was, I will explain later the whole concept, but this is just a brief schematic, graphical illustration that the release of nanotags from within the encapsulation of the nanogel can actually lead to significant Raman enhancement. So with this quantitative release, and also the increasing the concentration of the target virus, we can actually modulate the signal, the Raman signal of the nanotags, which can be used to quantify the captured target virus. So this actually, the design strategy starts with the coupling first of the preparation of your CES nanotags, where we have the molybdenum QD with the captobenzoic acid, which is the Raman probe, conjugated via EDC NHS chemistry, not indicated. So the same concept, EDC NHS chemistry, is also used in the functionalization of the surface of the magnetic nanoparticles, whereby we have the maleimide moiety and also the antibody functionalized. Then, as you can see, the hotspot engineering concept is that we can easily interact the nanotag with terminal tire groups to interact selectively with the maleimide moiety via the Michael addition process. This process is quite swift, takes place at room temperature and also at pH between 7.5 and 8. So with this strategy, we can easily attach the nanotags to this of the maleimide functionalized nanoparticles to derive some nanotag functionalized maleimide nano MPs, magnetic MPs. So after testing that, yes, we can anchor the nanotags very swiftly and quickly on the surface of the maleimide functionalized magnetic nanoparticles, we went on to use them as one of the components for the biosensor design in Raman in CES. So on the other hand, this smart delivery system is also one of the ways that we're thought of to prepare a material that we can encapsulate, we can use to encapsulate the CES nanotags. What happens usually is that the state-of-the-art method for protecting CES nanotags from interacting, for instance, with some human serum, extraneous materials, and a lot of other proteins and stuff in clinical sample, is to encapsulate them in some rigid silica shells. But this strategy actually blocks some light matter interaction, which is required for Raman spectroscopy. So the surface of the nanotags are not exposed to even the solution. So whenever they're in solution, they're encapsulated in nanoshells or in protective silica shells, which is the state of the art, or some polymeric material. So the idea was to advance this protective strategy by looking for a shell that can encapsulate the nanotags and also release them based on stimuli responsive triggering. So that the synthesis of the polymeric nanogel actually followed some electrostatic interaction process, and also what we refer to as the water in oils emulsion process. So using tannic acid and polyethylamine acid at controlled ratio, we can be able to fine-tune the surface property and also the internal framework of the nanogel to derive some stimuli responsive nanogels, which means they can exhibit some swelling and diswelling properties as you vary their pH. So this concept is also used for some kind of a drug delivery system, because in some environments, which is different, some target environments with known pH, you can actually design nanogels to carry some drugs or materials for you, so that whenever they are transported to the site of discharge, the pH that they encounter within that environment, especially in cancerous cell, can lead to the trigger release of the encapsulated material. So that's why we refer to them as payload or smart cargo, chemical cargo system. So this actually does demonstrate the encapsulation and re-encapsulation and discharge process of the nanogels at different pH. So mind you, this can actually be reversed, because you can have encapsulation at pH 7 and release at pH 4. You can also to release your nanoparticles depending on your design or your desired release and encapsulation pH. So that's why we refer to them as smart system. And I'll discuss later on the other prospects in nanogels technology that is being used to advance smart biosensing system and other fields as well. So basically, this is the scheme of the nanogel-based detection. Firstly, from this slide, after the encapsulation process of the nanogel at the pH 4.7 thereabouts, which of course we can still tune, it's not fixed. we can still tune the pH up to 8, but after optimization, we see that that pH is quite good, and it's also very desirous because of so we can have in the presence of the antibody, in the presence of the virus, sorry, the HEV or HEV VLP as the case may be, they can be captured by the targeting antibody. And also in the presence of the maleimide functionalized magnetic nanoparticles, we can form a nanostructure or sandwich nanostructure this way. This will then be isolated from the sample matrix or purified or concentrated as the case may be. And the fresh buffer solution and the pH is swiftly changed accordingly. Then with this, we see the release of the nanotags from within the encapsulated nanogels to directly go and bind to the maleimide functionality on the surface of the magnetic nanoparticles. So this kind of system sets up the hotspot region around the surface of the nanogel and very close to the target analyte, as opposed to being inside the nanogels. So with this kind of a system, we're able to achieve extraction or immunomagnetic separation and purification of sandwich immunocomplex, and also deliver some hotspot engineering sites where the nanotags, when released, can be recaptured and localized for sex hotspot, as opposed to them floating in solution and not having some anchor or base to for pure or effective scattering of light. So this system, after the whole sandwich and purification process, the whole CES experiment and measurement is now was now done on a 2D boron nitride substrate. So this has its own electromagnetic contribution, or sorry, some chemical and electromagnetic contribution to CES enhancement. So based on this system, we achieve some increase in the CES signal of the nanotags, which is dependent on the concentration of the target virus. And this kind of increase can be related to the concentration of the virus in the calibration with the calibration plot, whereby we can estimate the amount of the target analyte. So this whole study was actually done using the HEV virus-like particles, So the comparison of the results with was done by also carrying out the measurement on the usual bare glass substrates. So the usual bare glass substrate gave less sensitivity compared to having this material done on a pre-coated boron nitride substrate. In our earlier study, we've also used some nano structure or nanosheet of graphene oxide and the likes as the coating substrate where the CES measurement is actually done. So this is just to introduce an additional CES enhancement, either chemical or electrochemical, from also the 3D nanostructures, in addition to the one that is being delivered by the molybdenum plasmonic nanostructures. So this system was found to be highly sensitive and reproducible, which is one of the which is always one of the weaknesses of this Raman spectroscopy, because of the fact that you cannot really peg as to where the hotspot region is. It's very difficult for you to have reproducible measurements. You can scan certain area on the substrate, just like we show here. You will get some good Raman signal or CES signal. Then you scan another area, you will get little or no signal. But with this kind of localization of the nanotags using the maleimide functionality, we can see that we have a relative standard deviation of 5.95%, which shows some good reproducibility of the results. Then also selectivity, as been mentioned in LGC, is also very important for this system. But then this is also very quite obvious, because we use antibodies that are specifically used in targeting the desired virus, which in this case is HEV VLP. So we also did clinical studies using the HEV that is in cell culture supernatant. Then this same system was also used to detect norovirus by switching the antibody. So it means with this kind of system, we can design some universal kind of biosensor, which is not only for targeting virus, but also desired analytes, cancer cells, a lot of stimulant, antidepressant, even drugs, depending on how the biotargeting agent, desired biotargeting agent that you actually kind of use. So I would also like to discuss with us briefly, because the nanogels is actually not only responsive to pH, it's also responsive to other stimuli, which are also quite interesting for other studies and has been used quite widely. So one of the studies, the stimuli responsive based nanogels that have been designed and used and continue to evolve over time, or that will continue. The sound response reported, whereby in ultrasonic condition, there is a responsive or change in the morphology or change in the volume or change in the framework of nanogels, whereby they can actually release or trap desired materials or nanoparticles and can be used as payload system. Then also pH redox and enzyme responsive nanogels have also been reported. And also the electrically responsive nanogels are also been finding good application in electrochemistry and related applications. So this makes a nanogel very interesting sort of smart polymeric material that can be tailored according to desired application in different fields. So we've also found out that the new and emerging ways is the synthesis of nanogels using machine learning process. So supramolecular assemblies, different kind of nanogels can also be synthesized now.
Sorry, Dr. Ekado, please take care of the time.
Okay. So I'm done. I'm almost done now. So my conclusion and prospect is they can find application in self-powered system, implantable sensors for health monitoring, and also in vitro and in vivo studies, just like I've presented. So I'd like to thank my host supervisor, Professor Enoch Waipak, and also the Japan GSPS and Japanese government for the opportunity for research fellowship in Japan. Thank you.
Okay, thank you very much. Due to the time limitation, we just one question to ask. One question. Please check the chatting board. They have one question for you, Dr. Ekado.
Okay.
Or not one.
I have one question. It's a very nice talk, and I have a one question to ask. How to control the self-assembling structure of the quantum dots?
Is that the question? I think I'm seeing another question here.
How to control the self-assembling structure of the quantum dots?
How to control the self-assembly nanostructure? Well, you can actually. Are you referring to the molybdenum quantum dots?
Yes.
Okay, I think their control, you can actually control them based on the kind of maybe the solution controlled self-assembly. Yeah, and you can also control them based on surface functionality or surface functionalization. Like in this case, the use of PVP would actually lead to a reduction in self-assembly, surface assembly here. And other, so you can use some different kind of ligands. And also, in this case, I've also used glutaraldehyde or long chain ligands to actually control the self-assembly or surface assembly. Thank you.
Okay, thank you. Let's move to the next speaker. Next speaker is Yawen Liu from Shanghai University. Okay, thank you.
OK，已经点这个，然后点这个共享屏幕共享，这个。OK， 是不是没有开始
？Yes, start your presentation.
OK，dear Prof. Everyone, good afternoon. My name is Yawen Liu, come from Shanghai University. It's my great honor to have this opportunity to share my work in this meeting. My topic is magnetic platform based on self-assembly of magnetic nanoparticles with cancer cell membrane for faster detection of circulating exosomes. With my presentation my presentation was 3 parts. We all know that cancer is a major disease in our lives. According to the 2020 databases, there are many new cancer and death cases worldwide. Among them, colorectal cancer is the second cancer among the women and the third most common cancer among men. So therefore, early diagnosis of cancer has become an urgent clinical problem. And the liquid biopsy would provide non-invasive simple methods and can obtain information about tumor cells based on a new circulating biomarkers, including circulating tumor DNA, the circulating microRNA, and the circulating exosomes. The exosomes are a nano-sized EVs derived from endosomes, contain lipids, proteins, and nucleic acid. They have a double-sided phosphor membrane structure, which can be secreted from all types of cells and can exist in various body fluids. The tumor-driven exosome play an important role in tumor formation and migration. The engineered exosome mimics incorporating the required components of natural exosomes into synthetic nanoparticles, and using controllable procedures for assembling may be more acceptable. Through laboratory research, we found that the FN1 protein is highly expressed derived from colorectal cancer, and it can be specifically recognized and bind to the TNC protein. Therefore, magic nanoparticles with the cell membrane functionalized to specifically detect circulating exosomes. On the one hand, the magnetic properties used for simple enrichment. On the other hand, functionalized magnetic nanoparticles have faster response to the capabilities and the singular amplification functions. Therefore, our experiment plan is designed to carry out on the surface of the magnetic glycine carbon electrode. The first step is to incubate the magnetic nanoparticles and exosomes in the vitro, and During this process, the membrane coating the magnetic nanoparticles with excision antibodies are combined nanonature in complex matrix and then efficiently separated by the external management. Finally, the reacted magnetic nanoparticles are injected onto the surface of the electrode. If the solution contains the exotherms, the surface of magnetic nanoparticles after the reaction will binding the of exotherms and immunized on the electrode, and the golden nanoparticles of TNC can combine more FN1 protein and the resulting high signal. So the work that has been completed the first work we did was the extraction and separating of circulating exosomes. The NTA and the team confirmed that the exosome was successfully obtained. As shown in the page, the exosomes has a size of 1 nanometer. In order to evaluate the biological activity of exosomes, we use the SPR to test the constant of exosomes and the TNC. As shown in the figure, it is the 1.143 micron, which is several orders of magnitude larger than the value of 20 we investigated because the exosomes has a versatile structure, so the contact area between FN1 and the TNC protein is increased in the surface of the SPR medium. On the other hand, the overpressed FN1 protein on its surface, which can specifically bind to TNC protein. In addition, we studied the assembling of magnetic nanoparticles and enter membrane by UV, zeta, and FTIR. In addition, the ion-oxygen characteristic peaks appears in the FTIR. So this result supports the successful modification of antibodies on the surface of magnetic nanoparticles. Then the UV and the ERS also show the same results. So this material can be used for the further experiment. At the same time, we functionalized the surface, the golden nanoparticles and characterized the synthesized product. The figure demonstrates that successfully preparation of functionalized golden nanoparticles. In order to investigate the feasibility of the sensor platform, the detection strategy was first verified and analyzed. As shown in the figure, the red line is showed electrochemical signal after adding functional magnetic nanoparticles and exosomes, which increased significantly antibodies on the surface of exosomes. The blue line show electrochemical syndrome due to the combination of exosomes and TNC. Both the exosomes and the cell membrane handle electron transfer, increased ERS. The result is consistent with the proposed suggestion. Afterwards, we selected factors that will affect the performance of the sensor, such as the reaction time of the concentration of exosomes and the tyrosine functional quantum nanoparticles. First, the antibodies incubation time was optimized within 10 to 16 minutes. The electrochemical single of the EIS gradually increased, which may be related to the increase of the tyrosine surface coverage of particle nanoparticles and the membrane. When the reaction time is is 19 minutes, the electrochemical signal basically tend to be the same, indicating that the antibody body reaches a stratified state. So the 19 minutes is the best reaction time. Our further work is to optimize the concentration of tyrosine functional golden nanoparticles under the above optimized experimental conditions. The analytical performance of the constructed biosensor was tested by measuring the EIS response to different concentrations of exosomes. In the end, we want to detect the amount of the signaling application and accuracy of the sensor. That's all. My conclusion. That's all. Thank you. And it's our team's picture of taken on the Christmas dinner. Okay, that's all. Thank you.
Yes, thank you for your presentation. Any question, please? Oh, please check the chatting window. Okay, if they have any, don't have a question, we
Question
just
from student side first. Yeah.
yeah. Okay, you can use you just typing. Then we'll move to another presenter.
We can just keep the time.
Welcome. Yeah, let's welcome Hu Kun Liu from CAU. It's difficult to pronounce. Okay.
Thank you for your introduction. My name is Hu Kwang Min from Chungnam National University. So today my talk will be about let me check. Okay, so today our talk will be about the magnetoplasmonic co-shell. Wait. Hello everyone. My name is Hu Kwang Min from Chungnam National University. So today my talk will be about the magnetoplasmonic co-shell one-directional nanostructure, the synthesis, self-assembly, and also the application of the structure. So this work is cooperated with Ms. Ta-Chong Huang. So my talk will be divided into 4 different parts. First is the introduction, and also the synthesis of 2 different kind of nanoparticle, the magnetically coated silver nanowire, and also the magnetoplasmonic gold nanorod. And finally, we will talk about the application and the future prospect of the structure. So the heterogeneous nanostructure is the type of nanostructure that including 2 different constitutions. For example, in core shell nanostructure or also cathode slide nanostructure, you can see there is 2 different layers combining to make one nanostructure. And in my particular research, I focus on the one-directional heterogeneous nanostructure, which is including nanowire, nanotube, and also nanofiber. This structure is very special and unique compared to previously in today's talk we discussed a lot about general dimensional co-shell nanostructure. However, because the nanowire and nanorod, they have significantly higher surface area compared to zero-dimensional structure. Therefore, it's very potential in finding catalysts or also electrochemical application involving one-directional nanostructure. In the first figure, we can see some of the reported one-directional nanostructure, including nanospindles, nanorod, also nanotip. And these structures are very good as becoming physical sensor, because we can manipulate the conductivity, and also we can use the structure for making biosensor, and also by checking the vitals and biological properties. When you talk about the one-directional materials, usually we could assemble the one-directional material as a building block for building either two-directional and 3D nanostructure by using various methods. First is using shear force to induce the self-assembly of 1D nanostructure. And this method is very simple and widely reported already, but also having some certain difficulty. Depends on the type of nanoparticles and also the environment of using this kind of structure. Second method is for using the external magnetic field. This one is mainly focused in my research. So by applying the external magnetic field with the magnetically coated nanostructure, it will self-assembly by the flux of the magnetic field. Therefore, we can control the degrees of self-assembly by the strength of the magnetic field, and also by the length between the two polar of the magnetic field. And the last method is also, we can grow into two-dimensional and three-dimensional nanostructure by seeded growth during the synthesis of the one-directional nanostructure. So in this work, it's involved two different topics. First is the magnetically coated silver nanowire. This structure has been studied by some group already. And also, my second target is the magnetoplasmic gold nanorod. This one is the first, in my knowledge, I think it's the first reported structure synthesized by one-step method. So in the synthesis of the magnetically coated silver nanowire, we use a two-step method using polyosynthesis to achieve a very high yields and bulk synthesis of the silver nanowire in the first step. And then the iron precursor and also PVP is used at the sub-template of the iron oxide coated silver nanowire. Here is some of the electron microscopy images, including SEM and TEM images of the magnetically coated silver nanowire. We can see that the iron oxide, the magnetic iron oxide, is coated at the a thin layer outside of the silver nanowire, and the particle is easily attracted by the use of a neodymium magnet. And we also observe an 85 nanometer shift in the extinction spectra of the coated silver nanowire compared to the uncoated one, the black line you see in this graph. And in the XRD micrograph, we can see that the peaks of the iron oxide, the magnetite iron oxide, displayed by the blue line here, is observed in the XRD micrograph. So we have successfully synthesized the magnetic field responsive HFP204 nanowire using a two-step method. Next is the synthesis of the magnetoplasmic core shell core nanorod. So we have achieved like the first fully reported first one-step method for synthesizing the core shell core and iron oxide nanorod using polyo method. And this method also didn't rely on the CTAB for synthesizing the core nanorod, which is quite toxic to the biological environment. Therefore, it's suspected to be very biocompatible compared to other type of study core nanorod. And also, we can easily collect the nanoparticle using a permanent magnet in only a short period, around 5 minutes, to separate the magnetoplasmic core shell nanorod from the solution. The zeta potential is also showing that this type of nanorod is very high dispersed in polar solvent, including water or ethanol. By checking the same and time images, we found that the nanorod is somehow mixed in like around 70% to 30% of the core shell nanoparticle. Actually, that is one of the disadvantages of this one-step method. However, we saw that it's a very interesting result that when sonicating the sample, we can achieve like the uncoated coated in the some of the broken nanowire. And as you know, this tip maybe present some very unique property, including optical or also in plasmonic properties. So we will investigate this further in other research. By using XPS and also spectrophotometric method, we found that the shell of the core shell core nanorod actually is a mixture between magnetite Fe204 and also magnetic actually gamma Fe203. So it's in like around 1:2 ratio. But because two of the oxide are all magnetic oxide, so it doesn't affect much in the magnetic properties of the synthesized magnetoplasmic core shell core nanorod. By checking the VSM analysis, we found that the core nanorod, the coded core nanorod, actually is quite super paramagnetic, and also the retentivity is very low compared to other type of iron oxides. Also, the core stability show that the particle is very highly attracted to the magnetic field. So this type of magnetoplasmic material, one-directional core shell nanorod and nanowire, has been studied recently in various research involving the fabrication of the transparent film, and also in fabrication of the touchscreen, actually, in two of the research. So in my approach, I used the external magnetic field generated by two neodymium magnets opposite to each other to generate the parallel magnetic flux, and the sample is pipetted in between on top of substrate. So we will investigate the glass substrate and also the filter paper membrane substrate later. So by checking in the glass substrate using SEM, we found that the nanowire and also the silver nanowire and also gold magnetoplasmic nanorod is could be assembled using the external magnetic field in a very high degree of uniformity. Before and after, we see like a very significant change. As we know that the uniformity of the structure may generate the structural coloration of the substrate. Structural coloration is the cause of the observed color, not based on dyes or on chemical compound, but because of the structurally uniform substrate. For example, in this beetle, in the green line here, you can see that the when in the optical microscope, we can see that it made from repeatedly uniform surface, and also some of the naturally color matter is caused by the structural coloration. For example, in the wings of the butterfly and also in opals. So the structural coloration is caused by various effects, including the thin film interference, also in diffraction gratings, and also in scattering. So our assembled magnetoplasmic nanorod film made from the assembly of the gold nanorod, we observe the coloration difference by the observational angle between the substrate and the viewing angle, and also when rotating the film by parallel and by perpendicular to the assembled direction, we found that the color is significantly different as observed in the refraction spectrum here in the two figures, in both the glass substrate and also the nylon filter paper substrate. As in this figure, actually it's a video, so I don't know if video is playing now. So we observe that the color is significantly different when you rotate the sample by the phi here at 0 degrees and at 90 degrees, and also by rotating the viewing angle, we can create many different shape. Yeah, like in the playing video. And also, we found that the synthesized magnetoplasmic nanorod is also very potential for making a good catalyst because of the involving of both the gold core and also the magnetic shell make up iron oxide. So when we try to use the magnetoplasmic gold nanorod for the coloration of the rhodomine dyes, including rhodomine B and also rhodomine 6G. And we found that the mechanism for the decoloration is similar to a phantom catalyst, which is previously reported in the iron oxide nanoparticles and also in various iron-related substrate. And the plot here show that the speed of the degradation is kind of acceptable actually, and we will do further research to investigate whether we can accelerate the speed of the decoloration, and also we will check whether which kind of compound is generated before and after the degradation of the rhodomine dyes. So in the conclusion, we found that the large scale and also the bulk production of the AGFE-24 nanowire and also core-shell magnetoplasmic nanorod was achieved using the polyosynthesis, and the synthesized material show very unique opticals and also plasmatic properties, as well as the response to the magnetic field, and the self-assembly of the structure will be the key to unlock the potential electronic and also optics and a catalyst application as well. Yeah, thank you for listening to my presentation, and I'm willing to answer the question.
Thank you. Any question? Is there any questions?
Hello.
I have a question. I put it on chat already, but I just wanted to ask again. What is the role of the substrate in the self-assembly of the nanoparticles?
Yeah, for in our research, we found that the different in the glass substrate and also in uh, the nylon filter membrane substrate. I think we haven't checked the same images of the nylon filter substrate yet, but we think that is the degree of assembly. For example, in single layer or in multiple layer, they will be different caused by the thin film interference between the top layer and the below layer. Also, the substrate will have interaction with the nano rod or nanowire assembly during the drying of the sample, and also it will depends on the surface charge of the subject also.
Okay, thank you.
For magnetoplasmonic, is there any catalytic activity? So we have checked the catalytic activity of the subject here, and we found that it's act both in the Fenton reaction and also by using sonication as external energy source, or also light as external energy source, we can increase the catalytic activity of the reduction of the decoloration of the Roman dyes. But we have to study more to fully understand what is the main mechanism involved. Currently, it's a Fenton catalyst.
Okay, very good talk. Thank you.
Yeah, thank you.
So, yeah. So we finished the first session, and we will take a rest for 10 minutes. 10 minutes later, we will please come back.
We have only 5 minutes.
Oh, just 5 minutes?
Yes, just directly keep going. Let's keep the time. 그러니까.
Professor Lee.
Yeah.
Can I ask a question?
Yes, ask me.
I saw the nano silver nano line. Nano? How to say? Silver nano of nanoparticle. Just not he presented after the sonicating, the silver nano was broken. So I think
Yeah.
it will for the next nano road.
Yeah, right. We called nanorod. Actually, it was a very long here.
Yeah,
we want to separate them from some particles. Then some are just broken. The connection is not good. Yeah, some are broken.
Some, just some. So it's possible to make the wearable sensor using your nanowire.
At the moment, I'm not thinking about that direction. This is too much electronic engineering, so it's a bit far from my field of research. But yes, yeah, maybe later. But at the moment, no. No.
Okay.
Because it has also disadvantage, because our silver nano rod just covered with magnetic nano particles, so conductivity is not really high. Yeah, silver itself is better.
Very interesting.
There are too many chatting inside. Chatting is much better to understand, much interesting. I like this conference. Oh, so much. We may do every month.
Yeah, I hope so.
Yeah, it's just,
Our English will be improved.
I'm already improved. I don't care about the language. I'm talking about the research. I'm just quite interesting about the exogen binding magnetic nanoparticle. I just missed some part of her presentation, so I couldn't fully understand at the moment. But I just have some of the idea in my brain, and then her presentation touched that thing. So
You mean Ya Wen Liu?
yeah, right. Yeah, the previous
So you can
yeah,
ask.
Yahweh knew, right? Yeah.
How about we take this kind of work a seminar every month or every 2 months, like that?
Yeah, right. Yeah, that's what I want. Yeah, we can discuss later. Yeah, actually, students like it. Don't want to have this kind of seminar. The speaking Korean, speaking Chinese would be better for them, because yeah, speaking English is quite challenging.
But in case in your lab, maybe it's international level. English is.
Currently, just 90% are Korean, and they are afraid of speaking Korean. I'm speaking English. I mean, the lab is currently shifted from PNU to CNU. So yeah, most of them are just the master student, young student, chicken student, actually, young chicken.
No Chinese student in your lab now.
At the moment, very few PhD and all postdoc just leave. So it's kind of starting laboratory.
Yeah. Is there a Chinese student in your lab?
Last student left to Beijing. I mean, Chaifeng.
Telephone.
Yeah, we don't have Chinese at the moment. So if you have a good Chinese student, just let us know.
You
Always
pick
like
up one. You
I
can.
want to be a Chinese professor. I'm a professor in China. Why not? Yeah. Okie dokie. So we have to move to session 5.
Yeah.
Yeah, we have to wait for.
Hello, sir. Can you hear me?
Yeah, so I'm waiting for Dr. Park Sensei to
Yes,
enter.
sensei.
Coming.
Yeah.
Hi.
How are you, sensei?
I usually see you in the Facebook.
Already
Yes.
joined. Everyone.
Yeah, right. Yeah,
welcome
we,
to fifth session.
I think we've met about 2 years ago, right?
Maybe last in Okayama in a conference.
Okayama, right? Okayama University. Yeah,
Yes,
Okayama
sensei.
University. Yeah, right. Yeah, yeah, right. Yeah,
Okay.
Bioengineering
Let's
Society.
start fifth session for doctoral and master student. Okay. Talk time is a little different. This time 10 minutes talk, 5 minutes Q&A. Therefore, do not misunderstanding. First talk is from Shizuoka University, Dr. Pamida Nasrin, and title is Advanced Sensing System by Dual Functional Liposome for Chikungunya Virus Protein Detection. Can you share your file and go ahead?
Good afternoon, everyone. I am honored to have a presentation in this seminar. Thank you to all. I am Fahmida Nasrin. I have completed my PhD in Professor Park Lab and now continuing my research in the same laboratory. My research is focusing on the virus sensing, and I am going to present on advanced sensing system by using a dual functional liposome. In this work, I have used chikungunya virus as this caused outbreaks in Asian countries, especially in India, Bangladesh in last few years, and of course before COVID. And this virus has symptoms almost similar with dengue virus, so it is difficult to differentiate the infection. And as there is no vaccine and no medicine for this viral infection, so it is important to detect the virus at the early stage. Current now, the mostly used methods are RT-PCR and ELISA, which has some drawbacks like cost effectiveness or required longer time. So my target is to develop a biosensor which will be highly sensitive, selective, and rapid at the same time. So in this work, we have constructed a new model of liposome-based dual sensing system where we have combined the optical and electrochemical method simultaneously. So how liposome works for biosensor? We all know that liposome is a very good carrier for biomolecules. And if we see the structure of the liposome, there is inner hydrophilic core and the hydrophobic lipid bilayer in the liposome, which we can use for encapsulating probe. After burst out externally, we can have the enhanced signal from the liposome that generates from the encapsulated probes. So the advantage of this proposed biosensor is usually we use single probe for getting the fluorescence or any other signal. But if we can encapsulate a larger amount of fluorescent probe in the same system, we can get higher amplified signal. And also this system we have used magnetic separation, which can decrease the matrix effect of the impurities. And finally, we have combined optical and electrochemical methods together in a same system, so it can increase the sensitivity and more reliable detection system. Here is my experimental scheme. So first I prepared the dual functional liposome using the methylene blue inside of the liposome and the quantum dot, which is hydrophobic. So it was embedded at the lipid bilayer of the liposome. Then we have functionalized the liposome with the target antibody of the chikungunya virus. And simultaneously, we have also functionalized and conjugated the magnetic nanoparticle with the same antibody. And then we have mixed these two solutions with the chikungunya virus protein. And in the presence of the target, there will be a sandwich structure which is formed here. And after the magnetic separation and along with the using of the surfactant chloroform, we can get the disrupted liposome, and the methylene blue will come out from the liposome, which we can get the signal both in optical and electrochemical instrument. For the preparation of liposome, first I have mixed the different ratios of phospholipid with quantum dot, which is hydrophobic environment, and then I have made a lipid thin film layer, which is formed by using nitrogen flow. And here you can see there is a form of lipid film, which we can see under UV light, the fluorescence coming from the quantum dot. Then we have hydrated the film with the methylene blue solution, and after that we can get the liposome containing quantum dot and methylene blue. Here is the characterization data for the nanoparticles I have used. This is a TEM image for quantum dot, which is showing around 5 to 7 nanometer in size. And this is TEM image for magnetic nanoparticle, which is around 10 to 12 nanometer in size. And the confocal image of liposome showing the DIC image and also the fluorescence image. Here you can see the thin layer of fluorescence which is coming from the quantum dot, which we have embedded in the lipid bilayer. And the TEM image also showing the homogeneously distributed liposome. Then we have performed some optimization of this system, such as we have checked different surfactant for bust out the liposome, because some can be interact with the fluorescence of quantum dot. So we have to choose the best one. So after using several surfactant, we found the chloroform showed best signal for the fluorescence of quantum dot. So for my further work, I used chloroform. And also we have used different concentration of quantum dot for preparation of the liposome. As you see, as we have increased the concentration, the intensity of fluorescence also increased, but we only target the middle one, as we want the quantum dot only in the lipid bilayer. By doing all the optimizations and further, we have checked the system for detection of target virus. So at first, we have used fluorometric detection through the quantum dot intensity. Here you can see the fluorescence emission spectra has increased based on the concentration of virus is also increased. This is the calibration curve showing good linearity, and with the LOD of 0.56 picogram per milliliter level. After that, we have also checked the intensity of methylene blue through the electrochemical sensing system. And here we also got the signal based on the virus concentration and also the calibration curve showing the good linearity with the LOD of 32.7 femtogram per milliliter. So both the optical and electrochemical results we got showing the applicability of the sensor for the real sample monitoring. Selectivity is very important for any sensing system. So we perform the selectivity test of this sensor. And as this method have the magnetic separation, so the selectivity is also showing very good with compared to other virus. This is the target one for chikungunya virus. And from the comparison, we have checked our sensing system with some other sensing system. Unfortunately, for chikungunya virus, there is not so many sensing performance we could find. So this work can be a good alternative for using. So in the conclusion, we have developed a good liposome-based dual functional signal amplification system, which we can use for further biomedical applications, especially for chikungunya virus detection. Thank you very much for your kind attention.
Thank you for nice talk. How about this work? There's some question.
I have a question.
Okay.
Are the two nanomaterials bound to the same antibody? Are their binding site to the protein the same?
Sorry, can you repeat again?
Okay. Are the two nanomaterials bound to the same antibody? Are their binding site to the protein the same?
Thank you for your question. Yeah, the protein binding site is same, but yeah, as we have conjugated the antibody on the surface, so it is there are several antibody attached on the liposome. It should be, and simultaneously with the magnetic particle. So if the binding is same protein, but still it is fine to attach because there are several binding sites both on the liposome and also the magnetic particle.
Okay, thank you.
Okay, Dr. Nasrin, Professor Lee asked some question in your chat board. Can you find?
Just wonder, what are the meaningful level of concentration, limit of detection for clinical level of research? I think the lower, the better. I'm not sure.
Yes, Nancy, the LOD is as low as the sensitivity is higher. So
Okay,
we
then
always try to detect, or we always try to develop any sensor which can detect very low concentration of virus. So we can say that this is higher sensitive.
yeah, right. But in the clinical level, if a guy just infected only one virus, but the virus doesn't work with the human body, so we may need some accumulation. So we call the clinical level. So if it's too much sensitive, this is not a good sensor. So we may just consider in the real application with the human being. So that's the question. So useful for that sort of a sensor.
Yes, Sensei, thank you for your question. Yes, in some case, if the sensing system is very much sensitive, so it is also possible to have a false positive result. But definitely we should have to consider this for the real application.
Yeah, right. Yeah. Anyway, nice talk.
Thank you, Sensei.
Okay, another question from chat board.
Yes, we have checked the quantum yield, and for the quantum dot, I have used CDSE quantum dot, which is hydrophobic, and the quantum yield is nearly 50%. Thank you for your question.
Okay. The possible Dr. Nasani is not a real virus is a virus
Protein.
virus protein, right?
Yes,
Virus
sensei.
protein, not virus fighting, not virus.
Yes.
It's protein, right?
Yes, yes. For
Yeah.
chikungunya virus protein, we
Ah,
have
I see, I
used.
see, I see. Use the protein. I
Yeah.
see. Yeah, so.
We cannot get this kind of virus very rare. As
Yeah,
you
it
told, very rare
seems
one.
very dangerous. Isn't it?
Yes. Yeah. We cannot get this kind of real virus.
I understood.
Okay.
Thank you.
Okay, it's time up. Okay, thank you very much. Okay. Okay, we go to next speak. Next talk is from Shanghai University. Miss and Mr.
Miss.
Yes, Miss Chen. The title is the
Zi Chen.
dual signal detection of Parkinson's disease biomarker based on pseudo MF as an oxidized mimics. Okay, are you ready? Go ahead.
Hello everyone, my name is Jie Chen. I'm from Shanghai University. I'm very glad to have this opportunity to attend this conference. The topic I'm asked to speak on is dual signal detection of Parkinson's disease biomarker based on silver nano-coated morph as an oxidase mimetic. My presentation will include these four parts. Firstly, I would like to introduce the background of my research. Parkinson's disease is a common neurodegenerative disease which is caused by the death of dopaminergic neurons in the substantia nigra. As the population ages, the prevention of Parkinson's disease. More than 6 million individuals worldwide have Parkinson's disease. Currently, diagnosis of Parkinson's disease is based on history, physical examination. These methods have some shortcomings. For example, the earlier diagnosis rate is low, unable to distinguish Parkinson's disease from other Parkinson's traits. Therefore, in the earlier stage of the disease, a reliable biomarker accuracy. Alpha-SYN is composed of 140 amino acids and plays a role in regulate the stability of nerve membranes. It is related to Parkinson's disease. Study has shown that the level of nitrizated alpha-SYN in blood is related to Parkinson's disease. We want to build a method to realize the detection of nitrosylation alpha-SYN, which is of great significance for the diagnosis, prevention, and treatment of earlier Parkinson screening. More organic frameworks have attracted increasing attention in recent years. Furthermore, owing to their facial symmetries on the nanoscale and attractive functionalization via inclusion and surface chemistry, MOF is widely used in drug delivery, photothermal, heavy metal absorption, the detection of biomarker and antimicrobial activity. Most MOF exhibit activity of oxidase or pre-oxidase. Thereby, MOF is widely used in the detection of gluons, hydrogen peroxide, and so on. We want to synthesize a new MOF for dual signal detection of Parkinson's disease biomarker. Secondly, I would like to introduce the scheme in our research here. The established mechanical nanoparticles was functionalized with alpha S1 antibody 1. Silver nano-coated morph was synthesized by my 智慧猫 brother. It was functionalized with alpha S1 antibody 2. Functionalized magnetic nanoparticle as well as morph were added to the solution to the test. When there is a biomarker, they can specifically recognize the alpha S1 and form sandwich-like structure. Then the nano-conjugate is magnetically spread from its analyte medium because the level of nitricilate alpha SN is related to morph. We can make use of morph oxidize activity and silver nano to collect the electrochemical signal or colorimetric signal. Okay, now we move to the part of results. Firstly, we established magnetic nanoparticles is about 200 nanometer from team emerge. From the FTIR spectrum, we can clearly see the characteristic of amide and carbon hydrogen bond. Compared to the magnetic nanoparticles, it shows that the alpha SN antibody was successfully functionalized on the magnetic nanoparticles. What's more, the zeta potential was measured. This further confirmed the function of the magnetic nanoparticles. Secondly, we characterized the newly synthesized morph. From the same image, the size of morph is about 400 nanometer, and the silver nanoparticles can be clearly seen on the surface. EDC element mapping presents the composition of silver nano-coated morph. The element of carbon, copper, silver, silver were distributed on the silver nano-coated morph. Thirdly, oxidase-like activity of silver nano-coated morph was evaluated by using the TMB or ABTS as a substrate molecule to color remetric assay without the addition of hydrogen peroxide. Morph can catalyze the oxidation of TMB ABTS into oxidation products. The absorptions of oxidized TMB and ABTS was measured. This result indicate that morph possess the oxidase-like activity. When we optimize the action of condition characterized by morph, the best reaction temperature is 40 degrees. The best reaction pH is 4. As the concentration of morph and the TMB increasing, the absorptions of oxides are also increasing. What's more, kinetic for TMB characterized was monitored in a time scale mode at 642 nanometer. The relevant kinetic parameters were calculated according to the Maclaurin equation in order to investigate the specific mode of calculated activity of morph among the oxidized and pre-oxidized-like activity. TASS was performed. The results indicate that there is no pre-oxidized-like activity. To figure out the mechanism of the catalytic process, relevant free radical equations were used. The absence of the system with air histine reduced the significance, which indicates the production of single-electron oxygen. Therefore, single-electron oxygen is the reason that oxidizes the TMB in the catalytic reaction. Finally, we verify the feasibility of the experimental program in the colorimetric assay. The nano-conjugate magnetically spread from its analyte medium can catalyze the oxidation. In extremical acid, they also produce a clear extra chemical signal. Now we come to the last part conclusion. Silver-coated copper morph possesses the outstanding oxidize-like activity that can produce single-length oxygen, which can be used in calorimetric assay. Silver nanoparticles or morph can provide the electrical signal. That's all. Thank you.
Okay, thank you very much. Okay. Okay, somebody ask some question?
Nobody? Maybe me?
Okay.
Nice talk. So I just have wondering about your TM images about the nanoparticle, magnetic nanoparticle that show two different types of particle. So I feel a bit strange. So please check it later. And so you may not give the answer. And other guy asked a question. So my student bravely asked some question. Sejong, please ask by yourself.
It is silicon dioxide nanometers as a result of the strain speed during synthesis was not fast enough.
李教授的问题是你的那个磁纳米颗粒的 TIM 图显示是两种磁纳米，你放到这个 TIM 图上，磁纳米的，
One is magnetic nanoparticle and the other is silicon.
The other is what?
Silicon. The other is silicon.
Yeah, right. Yeah. So you developed the silica covered magnetic nanoparticle, and some are just a silica particle. Okay,
Yes.
that's fine.
Okay.
And there is another question from Sejong, CNU.
陈杰看那个 chatting 板上。
Your two questions from Sejong Park and also Indra, Mr. Indra. Can you read from chat board?
We use two morph. We use copper morph because of copper has a antimicrobial activity. We use
你用到的是催化。
Copper morph has antimicrobacterial properties. That's why, yeah.
Then other ions and
이건 어려워. 와, 이건 어려워. 와,
the activity of oxidase-like activity is depend on copper, and other ions also use the two. But we want to design a new morph copper morph, considering the copper has the antimicrobial activity, we use the copper morph.
Okay, Mr. Indra, it's okay? Okay, I have one important question. Your target analyte alpha synuclein is, I think, accumulate in brain, right?
Yeah.
And also, I think blood and the heart and tissue is very small, I think. Therefore, what kind of sample when you target from blood or some, I think from brain is difficult to sampling.
Yes.
We use blood.
Yes.
Blood.
Alpha S7 was found in the blood. Some research have reported.
Okay, in that case, colorimetric detection is a little problem because it's not so high sensitivity. Therefore, many people try to how to amplify the signal is problem. Therefore, okay, a very good target. However, it's best way is to take brain brain sample.
Yeah.
Okay. Other question? No? Okay, almost time. It's time. Time up. Okay, thank you, Miss Chen. You are very champion today. Okay, go to next presentation from CNU, Miss Mr.
Yes.
Miss Yong'un Che. Okay, Miss Che. This title is epi-based quantum dot for biomedical applications. Okay, already. Okay, go ahead.
Can you hear? Yeah.
Okay, we can hear.
Yes. Hi everyone, my name is Young-eun Choi, a master course in applied chemical engineering in Chungnam National University. And I'm working on the subject of quantum dot synthesis and application under Professor Jaebom Lee. Today I'm gonna talk about the iron-based quantum dots for biomedical application. The order of presentation is as follows. I introduce the quantum dots fundamentals and paper review, and then I'm gonna talk about the current research and conclusion. The keyword for my presentation topic is quantum dots. Quantum dot is a semiconductor particle with a diameter of 2 to 10 nanometer, and it refers to a particle with unusual electrical and optical properties. One of them is quantum confinement effect, refers to a phenomenon in which electrons form a discontinuous energy state by the space well when the particle is less than several tens of nanometers. And as the size of the space decreases, the energy state of the electrons increases and the energy of the electrons becomes wider. In particular, the energy level is quantized by the quantum confinement effect. And the energy band gap varies depending on the particle size. Quantum dots emit light in a specific wavelength range when exposed to light. The process occurs due to the excitation of photons, often referred to as photoluminescence. When exposed to light, the photons are excited and jump up to a higher energy level. After that, energy is released again and falls to lower energy level. This energy emits energy of various wavelengths depending on the size of the quantum dot. If the wavelength is in the visible range, it is the principle of emitting a variety of visible colors as energy type wavelengths. Like this, quantum dot with such unique characteristics are currently being applied in various fields such as diagnosis and bioimaging, display, and solar panels. Quantum dots which have been previous studies recorded very high quantum efficiency. You can observe this emit very bright and saturated fluorescent colors. However, most of the quantum dots have been researched previously used materials restricted by ROHS, Restriction of Hazardous Substance Directive. The use of the rare earth metals needs to be improved in terms of cost, and toxicity and surface modification needs to change for further application to various fields. In the case of indium phosphide, as a result of 3D scan, in which excitation and emission wavelengths bands can be viewed at once, emission of short wavelengths was observed even if the excitation wavelength band was changed. This is the basic light emission principle of quantum dots by quantum confinement effect. Unlike indium phosphide, the fluorescence 3D scan data of FESC quantum dots showed a slightly different pattern. Here, FESC is a new quantum dot material that has been researched in our laboratory for the past few years and is still ongoing. When various excitation wavelengths bands were given to QDs, it was observed that the emission wavelengths is varies depending on the excitation wavelengths. And through this, we will check the possibility of implementing RGB was confirmed. Let me explain once again the excitation-dependent emission property of FESC. Unlike other quantum dots, FESC quantum dots have a characteristic that the emission wavelength band changes according to the excitation wavelength band. This characteristic was well observed through the 3D scan and PR spectrum like this. And in addition, when looking through the femtosecond wavelength sweeping IR laser and the data patterned on a specific substrate, it was confirmed that various emission colors can be adjusted according to the incident light energy. I describe few papers that has been researched in the lab over the years. The first one is published in JAX in 2013. Is the world's first paper on the synthesis of iron-based quantum dots in organic solvent. We succeeded in synthesizing FESC and FESC2 quantum dot materials and recorded a relatively high quantum efficiency of around 20% with non-cadmium quantum dots. As a result of checking the TEM and XRD, it was possible to confirm the high monodispersity and crystallinity of the spherical quantum dot particles and the optical properties in the UV vis and PR spectrum result when the particles were irradiated with light in 365 nanometer range. A luminescence wavelength band of about 440 nanometer was observed, and like this blue fluorescent light was observed. By further supplementing of FESC and changing the complex synthesis process in the organic solvent, new FESC nanoparticle with a high quantum efficiency of about more than 40% in aqueous solution were synthesized in 2019. This result was published in Science Advances and succeed in bioimaging using FESC QDs with high quantum efficiency synthesized in aqueous solution. We succeed in synthesizing quantum dot and as a result of checking the PL spectrum, it was also confirmed that it has the characteristics of emitting 2 photons and 3 photon excitation properties. Before applying FESC to bioimaging experiment, the QD influence on cell viability was assessed by integrating the growth of different cell lines with FESC at various culture duration of QD concentration. The variation cell lines exhibited excellent viability in the presence of the QTs during 7 days of culture with more than 75% cell viability at the QT concentration of up to the 17 microgram per milliliter. To minimize non-specific binding during the assembly, FESE QT were encapsulated with polyethylene glycol (PEG) before conjugation with HER2 antibodies to form this structure, anti-HER QTs. HR2 is human epidermal growth factor receptor 2 overexpression in about 20% of breast cancer makes breast cell growth and divided in an uncontrolled way. Finally, high-depth fluorescence imaging of breast cancer tissue tracking was also successful using these quantum dots. Quantum dots are usually composed as a core and shell and ligand, and the core is the part where light actually emitted. The size of the core determines the emission wavelengths. The shell of the quantum dot promotes the quantum confinement effect of the core and determines the stability of the quantum dot. In general, quantum dots are synthesized in the form of a core and shell structure, and oxidation of the core can be prevented by using the shell, and the trapped energy level on the core surface can be reduced. Through this, quantum efficiency can be released by focusing photons on the core. Many research groups around the world are focusing on the core shell quantum dot synthesis, and many papers have been published in recent years. In particular, Samsung Electronics succeeded in synthesizing core shell quantum dot using indium phosphide and zinc selenide, published in Nature, a world-class journal, and applied it to display very well. So I'm synthesizing this core shell quantum dot using FESE particles. Zinc selenide and zinc sulfide hybrid structure, which are mainly used as a shell materials, and we are trying to synthesize a shell using two different anions. This is a schematic diagram. It's the synthesis process of FESE and core shell material using oleamine as a ligand material, and OD is used as a solvent. And the synthesis of core shell quantum dot is expected after 4 hours of reaction. The optical characterization in the UV spectrum measured after synthesis, high observance was observed at 365 nanometer for both bare and FEC and core shell materials, and as a result of calculating the band gap using this one, differences of about 0.5 electrovolt was confirmed. As a digital image of the solution of irradiating 365 nanometer light with UV lamp and result of the PR spectrum, we also confirmed higher quantum efficiency in core shell structure than bare FESE. Although there is not much data yet, we will succeed in synthesizing core shell quantum dots with more than 50% quantum efficiency through constant effort, and we plan to apply this to various fields such as display and solar panel as well as bio. Conclusion of biocompatible QD is with 2 and 3 photon luminescence properties were new synthesized using iron and selenium components, and in vivo live animal multiphoton imaging at a depth of up to 500 nanometer from the skin surface was clearly visualized to monitor tumor cells using a nonlinear femtosecond laser. Based on this study, we have synthesized a new core shell quantum dot which has secured the possibility of application not only in nanotechnology but also in other fields. Thank you for listening to the present so far.
Okay, thank you, great. Okay, thank you very much. Somebody ask some question?
Sorry, I'm from Sekiguchi.
Okay.
So, my question is very low-level question. How much cost reduction can be expected by the way?
Sorry.
How much cost reduction can be expected by the way? あの
You say cost issues?
Okay, sorry.
Please use the chatting window.
Okay.
Okay, right. Chatting board. Question?
Yes.
Okay, during communicating chatting board, other question if you have, please. Oh, here, raising here. How much cost reduction can be expected by this, reaction? Very difficult question, I think. Very complex reaction.
Compare the indium phosphide and FESC, the almost when I calculated almost 90%.
Okay.
Reduction. Very nice. 90% reduction.
Cost reduction is the indium phosphide. Compare the indium phosphide and FESC. When I calculated, I think 90% of the cost is reduced by the FESC. Compare the indium phosphide.
Okay, Sekiguchi, okay?
Okay, thank you.
Okay. Okay, other question? No? Okay, almost we have time, and also I think almost 10 minutes. Oh, almost okay, 7 minutes delay. Okay, it's okay. I think thank you very much. No question. Okay, thank you very much. Okay, we will. I closed the fifth session, and we have how about 10 minutes?
Yeah, 10 minutes break.
10 minutes break.
Yeah.
Okay. 16:35 from 16:35.
Yeah, 6:35. Okay.
35. Okay.
Yeah, take rest.
Right. Take rest. Okay.
Start walking.
누구한테 봤어? 토모랑 타카토미도? Two person?
Hello everyone, I'll present on this table. I use Cain-Parovirus CPV as a VLP capsid. It belongs to the genus of
돈 맞았어. 돈 아니 나는 군사 비용 비용 절감 계획. 비용 절감. 지금 쉬는 시간이 이제 35분까지. 힘들어. 괜찮아. 납대를.
너 보면
유광이 있으니까 이거 챙겨.
거의 끝났어. 이거
엄지만 그리고.
레스토랑 맞지?
레스토랑 맞아요.
네? 아니 여기
나 그러면 everybody 하자.
나 지금
또 홀로그램 다 보여 이제 여기 라인이 있어. 어디야 라인? 아니 원을 지워야 될 것 같은데?
아 여기까지? 오케이.
이건 넘버. 그다음에 넘버. 원을 지웠어.
사진 찍어줬다.
이건 no.
난 너. 너 짬이니까. 너 나치니까 너.
no.
너 아니야.
PT 가서 수정해도 돼요?
해볼까? 삐삐? 지금은 수정하지 마. 그냥 그대로
네.
뭐 귀엽게 넣는
귀여워. 진짜 발음 너무 어렵다. 퀀티테이티브 발음 어떻게 해?
퀀티테이티브?
네.
퀀티테이티브?
응.
정량?
네, 이거 pronunciation.
어? 뭐가?
pronunciation.
퀀티테이티브.
퀀티테이티브?
응.
근데 교수님이 quantitative 이렇게 말하는
퀀티테이티브.
quantitative. 약간 이게
퀀티테이티브.
quantitative 이렇게 하는 거 이거는 이거는
comparison. comparison.
comparison.
응.
comparison. comparison.
comparison.
comparison.
comparison도 괜찮아. compare 동사인데 comparison도 해도 돼.
compare밖에 안 썼는데 comparison. 이거는
mimetic. 체크해봐.
발음 너무 어렵지 않나요?
아니 그냥 뭐 우리 다 자펜, 차이나, 코리아 똑같은 아시아나 뭐
구글에서는 마하메틱이래요. 마하메틱. 미메틱이에요?
마메틱.
실수할까봐 무서워요.
다른 영상 준비했네.
근데 영상 해도
영상에도 마지막에 표현이 있어. 또 분명히 그치. 두 번째 언어는 뭐야?
네?
가정시에 배운 second language.
세컨드 랭귀지?
예.
코리안 잉글리시?
English 왜?
차이나.
배웠어?
네.
아, 그래서 고등학교 때?
니하오.
난 일본어 배웠어.
일본어요? 일본어는
오하요 고자이마스.
오하요 고자이마스.
이라사이마스.
아, 이라사이마세. 많이 들었어요. 횟집에서 초밥.
아, 횟집.
좋아.
또 오하요 고자이마스. 좋아. 원유가 데스. 원유가 데스.
영어도 배워서 오는데. 중학교 전화로 해가지고.
이 한국 사람들이 일본어 배우면 쉬우지.
그렇다고 하더라고요. 근데 저는 뭐지? 일본어 모양?
맞아. 거의 생각 안 해. 한국어로.
스프링 모양 그
아무도 배웠어도 히라가니가 카타카테 그 외울 수 없어.
히라가나 했던 가닥하다 노래.
카타카나 이거 외울 수 없어.
원성 뭐야? 마시멜로. 와, 이거 맛있더라.
마스크 벗고 해야 돼?
먹고 해도 돼.
쓰고 해야 돼?
쓰고 나서 어차피
쓰고 해야지. 일단 do you want some? 마시멜로. 슈가 코팅 마시멜로예요. 당 떨어져. You know? What this means? 당 떨어져.
당 떨어져 아세요?
당 떨어져.
랜 폴?
당 means
포도당 모르겠어.
like
야.
glucose?
glucose?
그래서
sugar? 당근?
So like tension is down. 근데 피랑 맵지 않아.
기분이 좋아져.
이거 미끌릴 것 같은 거
썼어요? 나 썼지로 냈지로.
저 언제 했어?
이번 정지 안 했어.
나는 오늘 하루 할줄 몰랐어.
설마 했지만 그냥 써서 보냈는데.
어제 기억나는데 봐서 못 썼어.
뭔가 1월엔 실험으로 인해서 바쁜 게 많더라고요. 다들 어제 실험실에 있던데. 그리고 연구생을 혼자
그게
있었어.
정말 다 이거.
다
미끌릴 것 같아. 하나씩 이거. 그 담주 월날에 항상 처음부터 끝까지
다 있는다고요?
교수님 가져가야겠다.
미쳤다. 지난번 안 썼는데.
쓸 건 없네. 다음 주에 많이 쓸 예정이에요. 한 6페이지.
이거 끝나고 지금 이번 시간 못했어.
근데 2시간짜리가 뭔가 더 색깔이 클리어한 것 같긴 해요. 물론 아니에요. 너무 예뻐. 근데 그 라이터리 너무 많아.
너무 행복해.
진짜 좋아. 내가
돌돌이 해도 많은 거야?
아니 오늘 아침에 돌돌이랑 시간이 없어서 안 나왔어.
그냥 어디 볼까? 파란색은 아니다.
이제 날씨 풀린 것 같아가지고 이거 하나
난 그냥 동네에서 쇼스를 갖고 왔지. 네, 제일 마지막.
it's almost time's up. So I have an announcement. We'll have a 10 minutes break after the final session. I mean this session. In the 10 minutes, please choose three. Hold on. Three presenters who collect the best presentation award. Choose them in the order of Korean side to Japan, Japan to China, China to Korea. Then a professor will announce the three best presenters in the closing ceremony. So thank you for great effort. So now it's time to have a final 6 presenters for short time. So please keep the time as much as possible. Then the first presenter is from Shizuoka University, Tomofumi Sekikuchi. Kuchi is talking about development and efficient antigen display system. So let's welcome him.
Hello everyone, I'll present on this tema. I use Cain-Parovirus CPV as a VLP capsid. It belongs to the genus of parvovirus and is a highly contagious infectious virus of dogs. The capsid is a virion structure, icosahedral particle with a diameter of about 20 nanometers, consisting of 60 copies of CPV-VP2. This is a part of the loop structure of VP2, which is exposed when forming the CPVLPs. The recombination with this part will lead to more efficient of displaying the target protein on the surface of the VLP. The STSC system is used for display. Aspartic acid of SpyTag and resin of SpyCatcher will form an amido bond. This figure shows the flow of EGFP binding the VLPs. Use this system. Our first construct is SC-EGFP that we added the SpyCatcher to the EGFP. The second is NSTVP2. We fuse the SpyTag with the N-terminal the VLPs. Use this system. Our first construct is SC-EGFP that we added the SpyCatcher to the EGFP. The second is NSTVP2. We fuse the SpyTag with the N-terminus of VP2. The third is LSTVP2. We attach the loop with the VP2. Then we expressed all constructs using silkworm expression system and purified them. The CPVLPs were confirmed by TEM and Immunotech. After confirmed, the CPVLPs were mixed with SC-EGFP, removed the unbound EGFP, and analyzed using CBB. These TEM results of LSTVP2 and LSTVP2 shows a similar size of VLPs, around 20 nanometers. The immunotherm result of CPVLPs of LST construct shows the binding between gold nanoparticle and the VLP. We assume the EGFP has bound to this part. The CBB result of purified mixed VP2 shows that LST bound more to the EGFP than to the NST. These results suggest CPVLPs of LSTVP2 is more efficient for antigen display compared to the other construct. Confirming the binding of EGFP using immunotherapy is recommended for future study. Thank you for your attention. Hello everyone, I'll present on this tema. I use
Ask some question to Tomoku. Yeah, so he prepared all video and audio, so very, very nice work. Any question from Korean and Chinese part? since it's too much bio.
It's a great work, Kat. I have a question. How do you extract the protein you extract from silkworms?
One more time, please.
How do you 解雇で発言するのか聞いてる。
解雇で発言する。
どうやって解雇で発言
I used baculovirus. ベクタープラスミド into
It's fine, yeah, it's fine.
Back-to-back system. I construct these genes into PFAS bug is vector plasmid, and vector plasmid into DH5, DH10 bug in include bacmido is baculovirus genome. So back to back and bacmido extraction and transfect cell.
Okay, did you understand the answer from the question? It's fine. Okay, thanks so much. Okay, thanks so much for the nice talk and Q&A. Let's move to the Chinese part. Shanghai University, Liu Hui Hu, and detection of alpha seen by SPR with nanogymeric signal enhancement. Let's welcome.
Okay. Dear experts, professional, good afternoon. I'm Ru Huihu from Shanghai University. I'm very honored to share my work at this meeting. My topic is detection of alpha SYN by nanolymatic signal enhancement. As mentioned above, Parkinson's disease (PD) is now a cause for concern. Native alpha SYN is a disease marker for PD, so my experiment chose nitrated alpha SYN as the target detection substance. Nanolene as a substitute of the nature enzyme has been applied to many fields, but the catalytic activity of nanolines has not been used in combination with SPR. So in my experiments, the nanolene was utilized to generate insoluble substrates, which results in a large change in the SPR angles. This is my experimental design, the PSC4. The PSC4 got the nanoparticles and the protein combined to form a network structure nanosem through hot gas recognition, and then the space cavity were used to bind with anti-alpha SYN through sandwich method. MUA was used to bind the natural antibody. The antibody can specifically identify the nitrification sites on the alpha SYN. Then the antibody was bound to the alpha SYN and the nanosems. Finally, TMB and hydrogen peroxide were added. TMB were catalyzed by nanosem generate soluble oxidation products, resulting a large change of SPR angle. The next were the experimental results. Firstly, the synthesized material was characterized. The experimental results showed that the antibody was successfully bound to the nanosem. This disagree proves the feasibility of the experimental. By electronic method, the concentration of the natural antibody was obtained.
And the conclusions, this sensor has a good feasibility on SPR nanolamps or synthesized for SPR single applications. The oxidation products of TMB result the SPR angle shift by changing the refractive index of the interface. These are the results of my present work. Thank you for your listening.
Very good talk. Please ask some question to her. No question. Dajong, do you have question to her? Or Tomokumi? Or you may ask through the chatting. Okay. Thanks so much for a good talk. And let's move to the CNU. Dajong Huang. She's talking about synthesis of magnetic and plasmonic nanogyne for sensing.
Hello, this is Dajong Hang, currently on a master's course in Professor Jaebom Lee at Chungnam University. Today, I will have a presentation about synthesis of nanozyme in sensing. This presentation will show that what is nanozyme and the several researches done with it. First, I will show what nanozyme is. Nanozyme is a combined word of a nanoparticle and enzyme, which means nanoparticle with the characteristic of enzymes. Nanozymes become biomimetic artificial enzyme, and by integrating the properties of catalysts and nanomaterials, nanozymes can be high biomimetic activity and stability and tunability, maybe multifunctionality. From recent paper, you can see that nanozymes are used in various ways. As you see this slide, magnetic nanobeads is used for amplification in an immune sensor. Here, they develop a nanocatalyst, applying it to cancer treatment. This enabled quantitative comparison according to nanozyme. So, in our experiment, we synthesized artificial nanozymes with controlled composition and structural dimension. The most important factor in this synthesis is to produce particles in uniform size and with a stabilized surface. We synthesize the particle through sorphotomal synthesis, as you see. Precursors are mixed and put into the autoclave for a while. After producing nanoparticles, surfaces are coated with silica and antibody to compose nanozymes. We also control the size and the surface charge. For example, 170, 107, and 230 nanometer. Also, we controlled the surface charge from negative to positive charge by changing stabilizer. Today, I showed that we developed nanozyme with AU or AG core with Epi203 or Epi3 shape, and that their size or shape and the surface morphology were successfully controlled. Soon, we are planning to sensing with fluorescence materials. We will develop novel metasurface nanozymes capable of detecting biomaterials. Thanks for listening. And if you have any question, please go ahead.
Thanks for presentation. Any question to her?
I would just like to ask a simple question. So, why do you think nanozymes are better than the natural enzymes?
Why nanozyme is better than natural enzyme?
Because nanozyme have many
Since nanozyme has such a performance.
because nanozyme have many advantages. Here, like here, high activity or high stability or low cost. This many nanozyme have many advantages, so we choose nanozyme.
Okay, very good effort. Thank you.
However, nanozyme has no specificity.
Yeah, that's the problem.
This is big problem.
I think that can control using surface or other method. So maybe it can prove maybe it can prove it. I think.
Therefore, you can provide the specificity to nanozyme.
Yeah.
Okay.
Usually by the bioassistant or using some surface modification. Okay, that's so good and interesting talk. And let's move to the Shizuoka University, Takafumi Nakanishi, talking about expression and purification of a white spot syndrome, virus antigen, blah, blah. Okay, let's welcome to here.
Good afternoon. Everyone, I would like to start my presentation. Good afternoon, everyone. I would like to start my presentation. Today, I am here to talk to you in shrimp industries.
What happened?
Good afternoon, everyone. I would like to start my
Nakanishi,
presentation.
what happened?
Today, I am here to talk to you about expression and purification of. Good afternoon, everyone. I would like to start my presentation. Today, I am here to talk to you about expression and purification of white spot syndrome virus antigen protein using silkworm expression system.
You can start.
WSSV was firstly reported in Taiwan in early 1990s and later had spread to other aquaculture regions, causing a huge damage in shrimp industries annually. Many studies revealed that this virus contains at least 5 major billion proteins, including VP15, VP19.
그럼 어떡하지?
Good afternoon, everyone. I would like to start my presentation. Today, I am here to talk to you about expression and purification of white spot syndrome virus antigen protein using silkworm expression system.
Oh, very good.
WSSV was firstly reported in Taiwan in early 1990s and later has spread to other aquaculture regions, causing a huge damage in shrimp industries annually. Many studies revealed that this virus contains at least 5 major billion proteins, including VP15, VP19, 24, 26, 28. Several studies have reported that these proteins can increase resistance to the WSSV. In this study, WSSV antigen proteins were expressed using silkworm expression system, purified and used as a protective agent in shrimp against WSSV. We first constructed recombinant plasmids expressing these 5 antigenic proteins using the back-to-back system. Biopsies were prepared from BN5 cells and were injected into silkworm larvae for protein expression. In here, these proteins were purified using frag affinity chromatography, and the results are as shown in this figure. Next, we used these purified proteins as a candidate protective agent against WSSV in shrimp. For shrimp experiment, purified proteins were single injected into shrimp. 20 days after injection, shrimp were challenged with WSSV and were observed for 20 days. Survival rate of VP15 and VP26 are increased compared with the previous group, and effects were lasting for 20 days. We have successfully expressed and purified 5 antigenic proteins using the silkworm expression system. Shrimp experiment suggests that VP15 and VP26 from silkworm can be a protective agent in shrimp against WSSV. Thank you for your
Very interesting talk. I never knew that the shrimp has got a white spot. Any question? And any question? Just my question is, if we eat the white spot, that will affect to human being? I'm just have a very interesting question.
中西君質問。
White spot may impact to human being? May not. I'm not sure.
Nakanishi kun.
Or directly just tell us by chatting. We can't hear actually. It's something disconnected. Sorry about it. We could solve it later because of the time limit. So please tell us the whole story about the human infection or other issues through the chat. And let's move to the Shanghai. Yongkai Lu about the detection of cancer bio based on the multifunctional peptide platform. Thanks so much, Kafumi.
Okay, thank you for your introduction. Okay, good afternoon, teachers and Good afternoon, teachers and students. My name is Lu Yongkai. It's my great honor to share my recent work with you. First of all, my work currently focuses on the detection of tumor marker PDL1 based on the multifunctional peptide platform. As shown, the peptide is divided into 4 parts. The first part is used to capture PDL1, and then second part is a connection part, which is used to connect the 2 peptides. And the third part is peptide with a benzene ring structure, which allows it to bond to a graphene oxide in a peptide conjugated manner. And it's an intracellular peptide of PDL1. The tail of this peptide has good hydrophilicity. It makes the interface will form a dense film of water, thus preventing the occurrence of non-specific bending. So it has an excellent unfolding effect. And we started with the glassy carbon electrodes, modified graphite oxide with good electrical conductivity. Then we used a design peptide to attach on graphite oxide electrodes. After the sensor was combined with PDL1, we then added the extracellular peptide of PDL1 to the electrode to realize signal amplification. And as a result show, the modification strategy of every step was monitored by electrochemical to verify feasibility. To sum up, we are aiming to develop a simple, inexpensive, and antibody-free biosensor for effective detection of the cancer mark PDL1. That's all. Thank you for listening.
Thank you for good presentation. Please ask some question to him.
Why did you use graphene oxide on the surface of GCE?
Because graphite oxide has a good conductivity.
Okay.
Any other question to him? Very good. Yeah, I also have questions. So, what about the anti-fouling effect of PDL1? So could you briefly tell us more about?
Sorry, I can't catch what you said. Could
Because
you please say that again?
I in the chatting space,
Okay,
or you can
unfolding effect of PDL1.
Yeah, you can tell me later.
Okay.
Yeah, in the meeting. Okay, then let's move
Okay,
to the.
okay. Thank you.
So much for good presentation. Yep, and then we are going to keep going on to CNU. Soyeon Saragang. She's talking about morphology control with a modified something particle, stopping for enhanced solar water splitting.
Okay. Hi, today I will introduce about morphology control with modified Golden malhematite photoanodes stopping for enhanced solar water splitting. I'm presenter Hui Soyeon Kang. I'm a master student of CNU under Jaevam Lee, and I'm co-work with Pajang and Yubang. So, okay. So I'd like to start by looking at why we need to develop hydrogen energy. Currently, the environmental pollution is issued. This is because the overuse of the energy is the major problem, which source is 96% fossil fuel. So the hydrogen production through water splitting using solar light energy is promising for substitution as clean and eco-friendly energy. The principle of the KC is when sunlight is incident to electrode in water, the electron of anode move to cathode. Then water is transferred to hydrogen and oxygen. However, water splitting has low efficiency of conversion from solar to hydrogen energy, like these three of challenges. So for overcoming these challenges, the catalysts need to be developed. So the purpose is to get higher efficiency. So in this subject, we use hematite to get higher absorption of sunlight. For this reason, the hematite has narrow band gap, so which is 2.1 electron volt, so visible range, and also other advantage. The purpose is to get high efficiency and durability. So the coating of catalyzed forms rough surface, which can decrease the reflection of the light and increase the absorption of some solar spectrum. For that, we choose the formation of nanorods. In comparison to nanoparticles, nanorods displays nearly 2 orders of magnitude enhancement of photocurrent. So therefore, it has higher light trapping and withstand more strain and reduced recombination. So let's get into the catalyst, what we use onto electrode. When you see the figure 1, for the hematite, which forms nanorods having core shell structure, which has 260 nanometer, like around, and 2.4 micrometer height. And in figure 2, the graded mark hematite is probed by XRD, and it has paramagnetic property by SCADE data. So the super paramagnetic property can ask to control alignment of the catalyst on electrode surface. So this is a key point to get higher solar to hydrogen efficiency. So this is the scheme of surface randomness dependence. So which shows we can divide it with 2, so which is with magnet and without magnet. So we are using 5 methods. So this is the result of the surface randomness dependence. The catalyst having best performance is the sample in the middle of 2 magnets, which is located at bottom of this one. So it has 35.6 milliampere per centimeter square photocurrent at 1.6 electron volt. So also you can see the same ordinance at figure 3b and 3c. So before I finish, I'd like to conclude by saying conclusion. So the main conclusion is to investigate alignment effect for enhancing efficiency of water splitting. The research needs for surface with different deposition methods and deposition technique. I would like to finish by thanking you all for your attention. Thank you.
Thank you for good presentation. Any questions are welcome.
Okay, may I question? One question. Okay, how about the reusability of material? Reusability.
Reusability.
Can be reused.
Yeah, like after.
You mean how many we can use the electrocatalyzed?
Like longevity, how long is going to be
예,
used?
2 times, 3 times, 4 times can be used one. Reuse one.
얼마나 오랫동안 사용할 수 있나? 1000시간? 1000 hour?
Yeah, but I need to check. Like.
Okay, okay.
Yes.
Usually just the catalyst. I mean, all of the catalysts just can be useful.
Yes, very important.
Over 1000 hours. So that's the one of the what's the just the super property of nanozyme. So we could use it in the energy solution. Good question.
Okay,
And the other question is the idea of coating nanomaterial under external magnetic force is very nice. Okay, thanks so much. Okay, now it's final. To Shanghai University. The Indian one, the evaluation of silver MOF nanocomposite for antibacterial finishing coating fabric. In the meantime, we will have the 10 minutes break after this presentation. Then please select 3 just best students. I know it's very hard to select, but we should. Sorry, there are something wrong with our computer. What should we do? How can we help you? Yeah, almost approach it. Yeah, so we can. Thanks so much.
Okay, teacher. Dear professors, good afternoon. I'm Indian Wang, come from Shanghai University. It's a great honor to share my work at this meeting. The topic I report today is evolution of move nanocomposite for antibacterial finishing cotton fabric. Masks can effectively prevent the new coronavirus, pneumonia, and other infectious diseases, play a vital role in blocking the interpersonal transmission of the new pneumonia epidemic. At present, most of the masks on the market are disposable physical protective masks, cannot kill the bacteria absorbed on it. So it's urgent to develop a kind of mask with sterilization function to prevent epidemia in the air from entering the human body. Therefore, we have developed a new type of antibacterial mask based on mental organic framework moves antibacterial material. So how is moves antibacterial? The release of mental ions and organic ligands to rupture. The bacterial cell content materials flow out and kill the bacteria, and moves produce reactive oxygen species rules kill bacteria. Next is my experimental protocol. First, I soaked the fabric in the antibacterial material solution, then dried and soaked it again in the solution. Repeated it 5 times. The emptied antibacterial fabric can be used for masks, surgical gowns, and protective clothing. Then reference to the isolation method in the national standard. I verified the antibacterial properties of fabric. First, the antibacterial fabric was added into aluminum flask containing bacterial fluid, shaken overnight. The bacterial plant culture was performed, and the member of color lines of the simple negative control was used to calculate the antibacterial rate. After the experiment, the minimum inhibitory concentrate mic of the antibacterial materials against Escherichia coli was found to 2.5, and against Staphylococcus aureus was found to be 1.25. The isolation method results shown that the antibacterial rate of the antibacterial fabric reached 99.99%, indicating that the antibacterial materials have great potential. So we can use MOVE-based antibacterial fabric for the development of masks and protecting clothing. So finally, it's the conclusion part. The antibacterial fabrics, like MOVEs, have good antibacterial properties. MOVEs can induce oxygen to singulate oxygen, which can kill bacteria. We can use MOVEs-based antibacterial fabric for the development of masks and protective clothing. That's all. Thank you.
Very tough. So, ask question.
Okay, very good mask. But how about the cost is very high? It's not high cost, producing cost.
Around $1.
$1.
$1 per one.
Oh.
We didn't calculate actually.
$1 per watt.
Wonder.
Suddenly, proposition appear.
Okay.
And Indra also has question. What is your opinion on silver MF antibacterial if we adopted it for antiviral properties? Yeah, also it's possible. I think it's possible to be commercial, but still it's so expensive. MF is not a cheap material. That's the big problem. Okay, so I also got one announcement. We have to show all of your face to take a photo for keeping. Okay, so before we finish, please turn on your video, and then some of the guy take a photo. Yeah. 멋있다. 이렇게 하니까. We say smile, or we say cheese, or we say what? Say cheese? Okay.
Cheese.
Yeah. So when you ready, please tell us. 아.
Smile.
Okay, from now on, now it's 5:20, so let's meet 5:30 with the 3 selected names. So we will have a ceremony. So see you later soon.
3 name be using chatbot. How to send 3 name?
Just you going to announce. The Professor Chen is going to announce. me going to announce, and Professor Park Sensei is going to announce 3 people.
Only
so
me.
you're going to just have meeting just for a while to select the 3 people.
I think okay. I'm saying chat board.
Yeah, maybe chat would be okay. Yeah, just anyway, in any way.
How to do?
Going to
okay,
select
directly I can send you.
Yeah, maybe. Yeah, just through the personal chat, and then send to me, and then I will announce the 3 people.
Okay,
yeah.
okay. I'll send you.
Yeah.
Okay.
Already you send me?
No. From now.
yeah. From now on.
No,
Yeah.
I'm writing. Okay.
Okay. I need to see my other student to discuss who is going to be the best Japanese the presenters. So please give me the 10 minutes.
Okay.
Or are you going to yeah?
I also need time. I will discuss with my students.
Yeah, that's important. Okay, see you later.
Okay.
봐봐. 누구 정해야 돼? 무서우니까. 너무 잘하는데? 잘하시는데? 그러니까. 힘들어, 일단 좀 하고. 그러니까. 발표도 잘하고, 영어도 잘하고, 대답 친구잖아요. 그럼 친다. 또. 여기 5분짜리 스크롤만 써놓으셔야 돼. 5분짜리. 영가지 어디도 여기 똑같아? 잠깐만. 이게 15분, 10분, 5분이니까 그럼 후반기에서는 뽑아야지. 후반기 여기는 다 뽑은 거야? 비중을 빼고. 이 정도는 저기 그냥 뭐 바쁘니까 안 해도 되잖아. 그리고 여기 정말 좋아요. 이건 아니 앞에 얘가 나왔던 것 같아요. 얘가 얘기 정말 잘했어. 이렇게 하는 거. 지금? 아니 이거 별별별별 먹어야지. 여기가 몰랐는데 근데 여기 발표에 금방 안 올리고 했었는데 애들도 잘 애들도 빨리 지금 애들도 빨리 지금 대국인데 Name from China. Inside. Smoke me.